Welcome guys to the Docker crash course. I am very happy to see you here. This crash course will help you to get up and running with Docker very fast. And here in this crash course I'll cover all key features of Docker, like images, containers, building custom images using Docker files, and launching multiple services using Docker Compose. Let me first introduce myself. My name is bstashchuk and I've been using Docker multiple years on practice for building real-world applications. And for example, I've utilized Docker Compose in order to start more than 10 different microservices. Also, I'm teaching online and there are hundreds of thousands of students who are already learning with me. You could find all my courses here at my website bstashchuk.com and go here to courses section. And by the way, there is Docker complete practical guide. It is more than 18 hours long, and this course is fully dedicated to Docker, and there I explain in details how to launch different containers, how to create necessary Docker files, and how to run multiple services using Docker Compose. So I more than welcome you to this Docker complete practical guide. Also, you could find all my courses at Udemy. By the way, I already got almost 10,000 reviews from my students, and almost 200,000 students are learning here with me at Udemy. And also, by the way, you could find here such course as Full Stack Web Development Bootcamp, where I teach how to build full stack web application from the ground up. And this course also uses Docker in order to launch multiple services using Docker Compose. So I welcome you to this course as well. If you want to learn other technologies, please check out my other courses here. If you want to connect with me, now here on the screen you'll see all links to my social media profiles. Please leave a like here under this video and please share it with your friends, coworkers, and spread this knowledge around the world. I will be more than thankful to you. Now let's get started with Docker crash course. Welcome to the Docker crash course. If you're a software developer, you should know what is Docker and you should use it during development of your applications locally on your computer. With help of Docker, you could very easily launch your applications inside of the containers. And even if you create multiple applications which should be run simultaneously, Docker could easily solve this task as well. And using Docker Compose, you could very easily and fast run multiple parts of the large, let's say, application. In this crash course, we will cover following topics. I'll explain to you differences between Docker and virtual machines. Also, I'll tell you what is Docker client and how to connect from Docker client to Docker server. We will discuss what are containers and how containers could be created. Also, there is a term images, and basically each container is based on a specific image. There are already created images which are available at Docker Hub, and also you are able to create custom images using Docker files. You could create a Docker file very easily locally on your computer and create corresponding image based on that created Docker file. And afterwards you are able to utilize this customly built image wherever you want. For example, you could launch containers locally, or you could push such customly built Docker image to Docker Hub and afterwards deploy it somewhere else. Also, we will briefly cover what is Docker Compose, and using Docker Compose you could run multiple containers just using single command. Let's get started. In order to use Docker, you have to install it on your computer. If you are Mac OS or a Windows user, you have to install Docker Desktop. If you are a Linux user, or if you want to run Docker, for example, on the server where you want to deploy your applications, you have to install Docker Engine. So, if you are a Mac OS or Windows user and want to use Docker in order to run your applications locally on your computer, please navigate to docker.com/products/Docker Desktop and download Docker Desktop. If you are a Linux user, please click on this link, and afterwards you have to select a corresponding version of the Docker engine for specific Linux-like operating system. for example Fedora, CentOS or other. After installation of Docker, you should see that here Docker desktop is running, and in my case it is running right now, and it usually takes some time in order to start Docker desktop very first time, because basically Docker desktop is a tiny Linux machine, and inside of that Linux machine, virtual machine actually, you will run all containers. So if Docker desktop is running, please go to Preferences here, and you might find settings of the Docker desktop. So here in the General section, you might choose how you'll start Docker desktop. For example, you could start Docker desktop when you log in. Also, if you go to Resources, you might set amount of the resources which Docker desktop might utilize on your computer. Here you could limit quantity of the CPUs, memory, swap size and disk image size. Please notice that all those resources will be shared among all containers which you'll run using Docker. It is very important. So if you allocate 2 GB of memory to Docker, then all Docker containers will share just 2 GB of RAM. Alright, afterwards, when you will start any containers, you could always go to dashboard and verify which containers are actually running. And for example, in my case right now, I'm running several containers like Mongo Express, API and others. Alright, now you have Docker desktop on your computer or Docker engine if you are a Linux user, and we are good to proceed. And next I'll explain to you differences between Docker and virtual machines. I'll see you next. Alright guys, let's now talk about differences between virtual machines and Docker containers. And there are actually advantages and disadvantages of using either virtual machines or Docker containers. And in different cases, you should choose different options, either go on with virtual machine or use Docker container. And I am sure that you have used before virtual machines a lot. And the virtual machine is basically an option to create a server with another operating system that differs from underlying operating system of the computer where virtual machine is running. For example, you could create a Mac OS virtual machine on Windows computer, or in opposite way, you are able to create a Windows virtual machine on Mac OS computer. And also very often virtual machines are used in the cloud hosting services, and you are able to rent a virtual machine for just a few dollars per month, and you will get access, for example, to any Linux-like system, and you are able to host your website or something else there. Alright, let's now dive more into details and talk first about virtual machines architecture, and also I demonstrate you how I personally use virtual machines. Alright, let's get started. Alright, let's start discussion about differences of virtual machines and Docker containers from talking about architecture of virtual machine. And let me first explain you this diagram, and afterwards I'll show you how I personally use virtual machines. Alright, so if you want to create a virtual machine, you should have either physical server or virtual server. It is basically possible to create virtual machines inside of other virtual machines. And there is host operating system. Host operating systems could be different, for example, either macOS, Windows or Linux, any operating system. Afterwards, on top of this host operating system, you should install so-called hypervisor. Examples of such hypervisors are following: VirtualBox, it is free and open source; VMware Fusion, for example, that is used on Mac OS, or VMware ESXi. And VMware ESXi is basically installed directly on the computer. It doesn't require any other host operating system. It means that there could be scenarios when hypervisor is running directly on physical server or other virtual server. Alright, on top of hypervisor, you are able to create virtual machines. And notice that main key idea here is that every virtual machine has its own guest operating system. And that means that you are able to create different virtual machines with different guest operating systems on another physical computer that is running different operating system. For example, host operating system could be Windows. Guest OS here could be Linux, guest OS here could be Mac OS. And every virtual machine has, of course, its own set of binary files, executables, own file system, actually dedicated resources like CPU, memory, hard disk, and so on. And of course, inside of every virtual machine, you are able to run applications. And every application inside of every virtual machine will be, of course, isolated from applications in other virtual machines. We could say that every virtual machine is a separate world, separate entity. And that means that if you want to get a complete separation of computers, virtual computers, you could of course use virtual machines, and you should use virtual machines. Alright, let me now demonstrate you how I personally use virtual machines. Basically, this computer that you see right now, it is Mac OS computer, it is actually virtual machine. And this virtual machine is running using VMware Fusion Hypervisor. Also, on this computer, basically my main computer is macOS computer with 16 GB of RAM. I also run other virtual machines on the same computer. And here, for example, you may see Ubuntu virtual machine. Here you could see Windows virtual machine. And again, all those three virtual machines are currently running on single physical macOS computer. Let me quickly demonstrate you how actually this looks like in terms of VMware Fusion and how actually resources are split across different virtual machines. But let me do that after the small pause. See you next. Bye-bye. Alright guys, now you understand the main idea behind using virtual machines. And it is that every virtual machine has its own guest operating system that of course may differ from underlying operating system that is used on main computer where virtual machines are running. And also usually every virtual machine has its own dedicated resources, like dedicated amount of memory, dedicated CPUs, and dedicated disk space. And now let me do for you a quick demo and show you how I personally use virtual machines for development and for recording of those courses. Alright, I use VMware Fusion, it is hypervisor for Mac OS. And basically at the end of a previous lecture I have shown you that I currently run three different virtual machines: Mac OS, Ubuntu and Windows. Of course, usually I don't run those virtual machines in parallel, and sometimes I stop two of them and run only single, for example Mac OS, or when I need, for example, Windows virtual machine, I start it and stop Mac OS. But it is of course possible to run all of them simultaneously. But I'll show you just in a moment what will happen if I'll start all of them simultaneously. My Mac OS will be actually almost out of memory. Alright, let me go to this page where I have actually a list of virtual machines that I'm currently running. It is Mac OS again, Windows and Ubuntu. And let me quickly demonstrate you settings, for example, of this Mac OS virtual machine. Go to settings and here go, for example, to processors and memory. And you'll see that this particular virtual machine has 2 processor cores assigned, and also it has 8 GB of RAM. There are also advanced options like enable hypervisor applications in this virtual machine, enable code profiling applications, and so on. With this option, for example, I'm able to create virtual machines inside of this macOS virtual machine. Alright, let's go back, for example, to configuration of disk. And here you see that I have assigned 46 GB of disk storage to this particular virtual machine. And all files for this particular virtual machine are stored in this VMDK file. Let me actually quickly go to this VMDK file and show its structure, and basically except this VMDK file there are a bunch of other files. Let me show in Finder, files for this macOS virtual machine, show package contents, and here you may see list of files for this particular virtual machine. And basically there are a bunch of different configuration files, cache files, log files, and so on. But the main files are here, this VMDK file and this one. Actually, I'm running here Catalina macOS operating system, and it actually uses two different disk drives, one for operating system and second for remaining files. And that's why here I see two different VMDK files. Also, it is possible to create so-called snapshots of virtual machine, and you see that there is single snapshot that actually also takes some amount of disk size. It is almost 9 GB in size. It is possible to create multiple snapshots and go back to a particular moment in time using snapshots. Alright, that's how disk looks like for this particular virtual machine. And total size of macOS virtual machine is 65 GB. It is of course larger than specified here in settings. Let me go to settings back, and actually again limit that was set for this virtual machine is 46 GB. Alright, let me also show you other settings like network adapter. You are able to add multiple adapters if you want, but here you see option share with my Mac, and in such case virtual machine will share IP address of my main computer. Next, you are also able to set some configuration parameters for display and so on. Alright, that's settings for this particular virtual machine. I could also quickly show you settings for this Windows virtual machine, and I have configured for it 4 GB of RAM and also 2 processor cores. Alright, but now let me demonstrate you how many resources are actually used at the moment at my main computer. And for that, let me open up Activity Monitor and go to Memory here and filter by VMware. And actually you'll see main VMware Fusion process. Here it is. It takes almost 300 MB of RAM, but also you'll see 3 different VMware VMix processes. This one, and this one. And basically at the moment every of those processes is responsible for running of separate virtual machine. And I have just shown you that I have allocated 8 GB of RAM to macOS virtual machine, and that's why here you see this process that actually takes this amount of RAM, 8 GB of RAM. And here next you see Windows virtual machine, and it takes 4 GB of RAM. And last one is Ubuntu, and I have allocated to it just 2 GB of RAM. It's pretty enough. Also, let me go to CPU tab, and also on this tab you'll see 3 different processes that are currently using some percentage of my main CPU. For example, this one is using at the moment 16% of my main CPU. That's how it looks in terms of resources consumption, and basically if I'll have a look again at the memory, you should see that my physical amount of memory on this computer is 16 GB, and almost 13 GB of RAM are currently utilized by those 3 different virtual machines. That's why it means that I'm not able to start 3 additional such kind of virtual machines, because my computer will be simply out of memory. Alright, also let me demonstrate you quickly that I have also access to ESXi server, that is actually hypervisor that is installed directly onto the server. And it is actually a remote server, and here on this server you may also see some virtual machines that are present there. For example, I'm able to access Ubuntu virtual machine, and I'm able to open it up and log into it remotely. Same I can do with any other virtual machines on this computer. Alright, let me also show you that you are also able to perform different management tasks with every virtual machine. For example, I could suspend virtual machine, I could stop it, I could reload it, I could create a full clone, and of course you are able to move virtual machine from one computer to another. And on production services like VMware ESXi servers, you are able to automate all those tasks. You are able to create, let's say, 10 clones from particular virtual machine. You could move machines from one server to another. You can scale machines and so on. It is really nice production solution. Alright, that's all for this demo. I hope you liked it, and the main idea that I wanted to transfer to you is that every virtual machine first has its own guest operating system and second has its own resources. And I have shown you that if I allocate particular amount of RAM to particular virtual machine, then this amount will be forever reserved at my main computer. Forever, I mean while virtual machine is running. As soon as I stop it, of course, those resources will be freed up. It is also possible to create virtual machines that actually share resources, share CPU resources and share RAM. And such approaches are very often used by hosting providers like Amazon, Google Cloud or DigitalOcean. And you are able to buy either virtual machine with dedicated resources, dedicated CPU, virtual CPU, dedicated memory, or you are able to buy so-called virtual machine with shared resources and share RAM and CPU with other virtual machines. Such virtual machines are usually much cheaper than machines with dedicated resources. Let me basically quickly show you that, and let me go, for example, to DigitalOcean. And here go to products and droplets. Every server here is called actually droplet. And if you'll scroll down a bit, you could see that there are so-called standard droplets and they share CPU with other droplets, and there are dedicated CPU droplets that have 100% dedicated virtual CPUs along with balanced memory. Alright, that's how it looks at hosting services, and again, most companies, most hosting services are using nowadays virtual servers instead of dedicated servers, and almost no one uses so-called bare metal or dedicated servers, I mean servers with physical memory, physical CPU resources and so on. Because of all advantages of using virtual machines. They could be easily scaled, migrated, copied, cloned and so on. Alright guys, I hope that you enjoyed this quick overview of my setup and now you completely understand what is virtual machine and what are advantages of using virtual machine. Let's now proceed, and next let me talk about architecture of Docker and advantages of using Docker, and of course about disadvantages of using Docker. I'll see you next. Bye bye. Okay guys, let's proceed with discussion about virtual machines and Docker containers and the differences between them. And we have before discussed advantages and disadvantages of using virtual machines, and I have made for you a small demo. Now let's go on and let me demonstrate you now this diagram where I have outlined the structure of Docker and Docker containers. First of all, there is the same as with virtual machines, physical server or virtual server. Next to it there is host operating system, like Mac OS, Windows or any other Linux-like system. Next there is Docker engine. And on top of Docker engine there are containers, and on this diagram there are two containers, container 1 and container 2. And notice that main difference of this architecture from architecture with virtual machines is that the containers don't have their own guest operating system. They have only binary files, libraries and some applications that are running inside of every container. But again, main idea is that there is no guest operating system. And of course, out of this fact comes the conclusion that containers somehow need to use underlying operating system. And that is the responsibility of Docker engine to perform such communication between containers and underlying operating system, host operating system. That's how containers are structured basically. Alright, let me now show you how Docker desktop looks like on this computer. I have actually installed it, and you should have also installed Docker on your computer. If you have Mac OS or Windows, you should have Docker desktop, and if you have Linux-like system, you should have installed Docker engine directly on your computer. Alright, let me go to this icon, and I see that Docker desktop is running right now, and let me go to dashboard here. And on the dashboard, let me open up settings, click on this icon and go to resources. And here on this page, I see resources that were allocated to Docker on my macOS computer. And I see here amount of CPUs, 1 CPU, and amount of memory, RAM. And there are just 2 GB of RAM allocated to Docker. There is also swap size equal to 1 GB, and the total disk image size is 60 GB. And at the moment, only 9 GB out of 60 are utilized. These are resource limits for Docker setup on my computer. And now question, what if I run, let's say, 10 containers on this computer using Docker? How many resources will be utilized by those containers? Answer is very simple. Here are limits. In total, all 10 containers cannot use more than 2 GB of RAM and more than 60 GB of hard drive space. These are limitations for all containers that you could run on your computer. And it means that all containers basically share resources that were allocated to Docker. CPU resources, hard drive resources, and memory resources. And that is the main difference between virtual machines and Docker containers. And of course, you are not able to run inside of the Docker container, for example, Mac OS operating system or Windows operating system. It is not possible at all. Because again, as I have just shown you, Docker containers don't have their own guest operating systems. They have just processes that are running on top of host operating system. That's it. But now you may ask me a question. How it is actually possible to run containers on Mac OS, on Windows, and on Linux? I'll answer this question in the next lecture, but before wrapping up this one, let me quickly go to Activity Monitor and show you actually how many resources are utilized at the moment by Docker on this computer. Activity Monitor. And let me filter all processes by keyword Docker. And here on top of this list you see process called com docker hyperkit, and it currently uses around 2 GB of RAM. And that's exactly that amount that was assigned to Docker in Docker settings. Let me basically quickly go to Docker setup, go to dashboard and settings and try to increase this size. Go to resources and let me make it, let's say, 3 GB and apply and restart. Alright, Docker was restarted. Let's close this window and go back to Activity Monitor. And now I see that Docker hyperkit is utilizing around 3 GB of RAM. Except this process, you see here such processes as Docker, com docker VPN kit, com docker backend, supervisor, and OS6FS. And all those processes are actually for interaction between Docker engine and my main macOS computer. Alright guys, that's all for this lecture, and the main outcome is that every Docker container does not have its own guest operating system, but has own processes and doesn't have own resources. All resources are shared between all containers. Next, let me explain you how Docker containers could be running on different operating systems like Windows, Mac OS, and Linux. I'll see you guys in the next lecture. Bye bye. Alright guys, now you know differences between virtual machines and Docker containers, and main difference is that virtual machines have guest operating systems, and usually every virtual machine has dedicated resources like CPU, RAM, and hard drive. Docker containers don't have own guest operating system, they rely on host operating system, and they also don't have dedicated resources. They share resources that were assigned to Docker engine. Alright, let me now explain you how actually Docker containers are running on host operating system. And let me show you this diagram. And on this diagram you see Linux as host operating system. This machine has some resources like CPU, RAM, disk, and network. There is also Linux kernel. Inside of this Linux machine there is Docker engine installed. And thanks to Docker engine, now you are able to create different containers inside of this Linux machine. And all those containers will be sharing those resources. Actually, you could limit resources that could be allocated to all containers, and of course they should be less than this machine has in total resources. I mean, if this Linux machine has, let's say, 8 GB of RAM, you could assign to Docker containers just 2 GB or 3 GB. And again, all those containers will share those resources. Share disk size, share access to network, share RAM, and share CPU. It is possible in Linux operating systems because in Linux it is possible to group resources per process or per group of processes. It is not possible to do in macOS, for example. But it is possible to do the same on Windows computers, and it is possible to create Windows containers. And again, main idea behind all of this Docker setup is that it is possible to group resources CPU, RAM, disk network per process inside of container, or per group of processes inside of container. For example, you are able to run 10 different containers with Node.js process. And every container may run different versions of Node.js. Or you are able to create 10 different NGINX web servers in 10 different containers. And again, use different versions of NGINX, different set of HTML files, JavaScript files, and so on. Again, it is possible due to separation of processes inside of the Linux. But now question, how is it possible to do the same on macOS computer or Windows computer? It is possible if you'll create very small, tiny Linux virtual machine inside of macOS or Windows computer. And in such case, picture will be exactly the same, but this Linux virtual machine will be running all containers inside of the Mac or Windows computer. That's that simple. Alright, let me now explain you how actually containers interact with Linux kernel and use resources on Linux computer. But again, main outcome from this lecture is that containers, Docker containers, are running inside of the Linux machine. And if you set up Docker desktop, you install actually tiny Linux virtual machine on your Mac OS or Windows computer. Alright guys, let's proceed, and next let's discuss how Docker processes interact with Linux kernel and use resources. I'll see you in the next lecture. Bye bye. Now you know that Docker containers are running actually at Linux host operating system. And if you install Docker on Mac OS or Windows, you install application called Docker Desktop. And it actually creates small Linux virtual machine, and inside of that small Linux virtual machine, containers are running. Let me now explain you more details about how containers processes interact with resources like CPU, RAM, and memory. Here on this diagram you see Linux host virtual machine. Every Linux has Linux kernel, and it has usual resources like CPU, RAM, network, and disk. If you install Docker engine on Linux, it will actually install some processes that will be able to create separate resources like separate disk space, separate processes for every container. And it's possible in Linux due to namespacing. Namespacing allows you to create separate users, separate processes, separate spaces on hard drive that will be completely independent from each other. And on this diagram you see that every container, this one, and this one, have separate space on hard drive. And there are separated container 1 files, container 2 files, and container 3 files. Before going on, let me actually ask you a question. What is actually computer? Computer is basically a set of hardware like CPU, memory, hard drive, and network interface or interfaces, and a set of files. Nothing else. And when you power on computer, some of the files become actual processes that start in memory. And afterwards, processes are running, they access hard drive, access memory, access CPU, create additional files, and so on. But in a nutshell, every computer is simply a set of files and set of processes when computer is running. Same picture is with containers. Every container, when it is stopped, has only set of files on a hard drive of the Linux computer. When container starts, some of the processes are started in a Linux machine. And those processes interact via common Linux kernel. And they interact with resources like CPU, RAM, and network. And they may take some part of those resources. And please note that by default, Docker containers don't have any resource limits. And that means that every container may utilize up to 100% of all resources allocated to Docker Engine. And if you install Docker Engine directly on Linux computer, it means that every process in every Docker container may take up to 100% of all resources of Linux machine. If you use Docker Desktop on Mac OS or Windows and allocate some resources to Docker Engine, then those are the limits that could be utilized by every single process inside of every container. But of course, it's possible to limit resources for every container. And it is possible in Linux by using C groups, control groups. And you are able to say that, for example, container 1 may not use more than, let's say, 512 megabytes of RAM, or half of CPU, something like that. Alright, main idea behind all of that is that every container has own processes. For example, here in this container 1 there is single process, container 2 has also single process, and container 3 has two processes. But usually containers in Docker have single responsibility, single purpose. And that means that the best case is that every container is running only single process. For example, let's say that you want to launch Python application inside of the Docker container. And this Python application needs access to Redis database and write some records to it. Also, it needs to have access to mail server in order to send some emails. You could create a single container that will be running three different processes: Python, Redis, and mail server. But this solution is bad in terms of scalability and manageability. It's really hard to manage such kind of containers. And that's why it is much more better to create three different containers, one process per each: Python, Redis, and mail server processes. That is a single responsibility principle. And in such case, you are able to manage every container independently. You could upgrade every single container, you could scale containers and make, for example, 5 containers instead of 1 and create load balancing across different containers and so on. That's why main idea in Docker is that you should run single process per single container. Alright, that's how containers interact with resources on host machine. And this machine that is running containers is called Docker host. Next, let's proceed and let me explain you main components of Docker. And main components are actually Docker client, Docker host, and Docker server. I'll see you in the next lecture. Bye-bye. Let's proceed, and now let me briefly overview main Docker components. And afterwards I'll go through every of them in greater details. Alright, Docker client. Docker client is used for execution of commands on Docker server. And basically when you open up terminal and enter Docker command, you launch Docker client. Next, Docker host. Docker host is used for launching and storage of containers. And actually, if you run Docker Desktop on Mac OS or Windows, then Docker host is small Linux virtual machine that is running on top of Mac OS or Windows computer. If you have installed Docker Engine directly on Linux computer, for example Ubuntu server, then this Ubuntu server is Docker host. Next, Docker server. There is actually no such kind of single Docker server. Basically, it is a set of different processes that are responsible for creation, management, and execution of different containers. And that is called Docker server. And for example, part of Docker server is Docker daemon. and Docker client connects to Docker daemon in order to send to it different commands, like docker run or docker images or something else. And those commands are executed afterwards by other processes at Docker server. For example, there are processes called containerd or runc that are responsible for creation and management of containers inside of the Docker host. That is a Docker server. Next, Docker image. Docker image is used for creation of Docker containers. It is read-only set of files, and you are able to create your own images or download already created images, for example, from Docker Hub. Docker container is running based on specific Docker image, and you are able to create multiple containers from the same Docker image. Next, Docker repository. Docker repository is a set of Docker images with different versions. And you are able to create custom repositories, you are able to use already published repositories, and so on. And place where Docker repositories are stored is called Docker Registry. And most popular Docker registry in the world is Docker Hub. It is actually similar to GitHub. At GitHub you store Git repositories, at Docker Hub you store Docker repositories. Alright, that's all for quick overview of Docker components. There are basically other components, like for example Docker Compose, but I'll talk about them a bit later in this course. Now let's make a deep dive into every of those components, and let's start with Docker client. I'll see you in the next lecture. Bye-bye. Let's now start discussion of Docker components in greater details, and let me start with Docker client. Please open up terminal, and if you have Docker installed on your computer, then you should have Docker command available in the terminal. Please type simply Docker and press enter. And basically you have just launched Docker client, but afterwards this process has exited. And here in this output you see list of available commands you are able to use at Docker client. For example, here you see set of management commands like container, image, network, node, plugin, and so on. Also you see list of commands like cp, create, exec, ps, and so on. And basically there are alternative commands. For example, you could enter either docker ps command or alternative command docker container ls that actually performs same action as docker ps. Let me quickly show you that. Let me clear terminal and type docker ps and type docker container ls. And actually result is the same. Again, I have just launched Docker client, and it has connected to Docker server, Docker daemon specifically, and executed some commands on Docker server. Also, you are able to check version of Docker client using docker version command. And here, if you will scroll a bit up, you see information about Docker client. Docker client at the moment at this computer is Docker Engine community. Actually, same information you see here in server section, but we will talk about server in the next lecture. For now, please focus at client section. Its version is here. Of course, in your case, version may be different. API version, Go version, basically client and server are written in Golang. And here you see Golang version that was used for client and server programming. Next, after this line, you see git commit SHA hash, and actually same hash you see here in server info. And that means that Docker is basically available as GitHub repository. And here on this line, you see SHA hash of the last git commit in that repository. Next, you see when this client was built and its underlying architecture, Darwin AMD 64. Also, you see here that experimental features are disabled. That is a client information. Let me now quickly stop Docker Desktop. Simply go to this icon and quiet Docker Desktop, like this. And let me execute same command once again, docker version. And now, same as before, I see information about Docker client, but instead of information about Docker server, I see error cannot connect to the Docker daemon at Unix var run docker.suck. Is the Docker daemon running? And the reason for this error is that I have just stopped Docker server, but I am still able to start Docker client. And the reason for that is that Docker client is simply separate binary file on my computer. Let me quickly show you location of this file, ls user local bin. And here is this executable file. Except Docker, you are able to use other binary files like Docker Compose, Docker Credential Desktop, or Docker Credential OS6 keychain. For example, using Docker Compose executable file, you are able to start multiple containers simultaneously from Docker Compose file. We will talk about that later in this course, and of course, we will launch containers using Docker Compose. Alright, that's information about Docker client, and all what you need to understand is that Docker client is separated from Docker server, and it is used for execution of commands on Docker server and getting output from it. Great, that's all for this lecture, and next let me talk about Docker server. But first let me start over Docker again, and see you in the next lecture. Bye-bye. In the previous lecture, I have shown you what is Docker client, and basically it is a separate executable file located on your computer where you have Docker installed, and with help of Docker client you are able to connect to Docker daemon and send some commands to it. For example, you could say, please start a container with Ubuntu image, or please list images, and so on. Just sending commands to Docker server and getting some output from it. Now let me talk in details about Docker server. Docker server is actually a set of different processes, and Docker daemon is one of them. Let me go back to terminal, and here last command that I have executed was docker version, and I have shown you that when Docker server is stopped, we will see such error, cannot connect to Docker daemon. Now let me execute same command once again, because now Docker server is running again, and here in this output you see several blocks. First block is information about engine. Here you see its version, it actually matches in my case version of the Docker client. Also next you see API version, and basically this API version is important for communication with Docker client, because Docker client communicates with Docker server via API. Next you see Golang version, because again server and client are written in Golang, and both server and client are available in GitHub repository, and here you see same last git commit that was used for this repository at GitHub. Next you see build date and underlying OS architecture, and here in this output you see Linux AMD 64, but Docker in this case on my computer is running on macOS. But here you see OS architecture Linux. And that's what I have told you before. If you run Docker on macOS or Windows, Docker creates small Linux virtual machine. And that you see here in this output. Next you see information about other processes that are running on Docker server, like containerd, runc, and Docker init. This process, Docker init, is responsible for start of the Docker server. This process is responsible of creation of containers at the high level. But at the low level, it communicates with runc process, run container. This process works closely to Linux kernel, and it is responsible for allocation of resources to containers, for management of processes, and so on. And again, Docker server is simply a set of different processes. Alright, let me now quickly switch to Ubuntu server and enter same command here, docker version. And I'll see similar output. Here is information about Docker client, and here is information block about Docker server. And in my case, here at this Ubuntu computer and here at this macOS computer, Docker engine version is the same, 1903.8. But difference is that here Docker engine was installed directly on this Ubuntu computer. And on macOS there is Docker desktop that has created additional intermediate small Linux virtual machine. Alright guys, that's all for this lecture, and next let's discuss what is Docker host, and I'll demonstrate you what is Docker host on macOS computer and Ubuntu computer. I'll see you in the next lecture. Bye bye. We have just discussed such Docker components as Docker client and Docker server, and you are able to get information about those components using docker version command. And basically now you know that the Docker server is set of processes like Docker daemon, containerd, runc, and Docker init. And again, if you go back to terminal and enter Docker version, you'll see information about those processes here. But no question, where those processes are running? They are running at Docker host. But what is Docker host? Let me go back to this diagram. If you install Docker Engine directly on Linux computer, then this Linux machine is Docker host. And all processes of Docker Engine are actually running at this Docker host, at this Linux machine. If you are running Mac OS or Windows, then, as I have told you before, you'll install tiny Linux virtual machine on top of Mac OS or Windows computer. And this Linux virtual machine will be actually Docker host. And inside of this Docker host will be running same processes as dockerd, runc, and so on. And all containers will be created inside of this Docker host, Linux virtual machine. And those processes that are running inside of the Docker server communicate very tightly with Docker host. For example, processes create new networks at Docker host. Let me demonstrate you that. Let me first switch to Ubuntu virtual machine, this one, where Docker was already installed, and let me type here command ifconfig like this. And I'll see here such network interface as Docker 0. And its IP address is 172.17.01. It is actually default gateway for all containers that are created in default bridge network. At this computer, Ubuntu computer, there is new network interface called Docker 0. And it has this IP address. And all containers that will be created on this host, Docker host, will communicate with this IP address as default gateway and go to internet via it. For example, let me quickly create a busybox container, docker run-it busybox, and here, unable to find image busybox latest locally, let's wait a bit, it will download the busybox image from Docker Hub. Okay, image was downloaded, and here I could enter command host name -i, and I'll see IP address assigned to this container. And notice that this IP address is from the same network as this IP address of Docker 0 interface on this Ubuntu computer. And this actually proves that this Linux computer is Docker host. Alright, let me now go back to this computer, macOS computer, and go to terminal here. And let me clear it first and type ifconfig. And here in this output, I will not see Docker 0 interface. That's because this macOS computer is not Docker host. Instead, tiny virtual machine, Linux virtual machine, is Docker host. But now you may ask me a question: how we are able to get access to Docker host on Mac OS or Windows computer? Let me demonstrate you that quickly. Let me clear terminal, and here in the history I have such kind of command. Now I will not explain you what this command does, but with this command you are able to get access to this virtual machine that acts actually as Docker host. Let me press enter. And now I am inside of this virtual machine. Let me type ifconfig command. And here in this output I'll see Docker 0 interface. Same interface as I have seen here on this computer, with same IP address 172.17.01. And that means that Docker host on Mac OS and Windows computers is actually Linux virtual machine where all containers are created. That is Docker host. And inside of this Docker host, all processes like containerd, runc, and Docker daemon are running. Wonderful. That's what is Docker host, and now you should understand actually what is the difference between Mac and Windows and Linux computers, where Docker Engine is installed. Let's now proceed, and next let me talk about Docker image and Docker container. I'll see you next. Bye bye. We have just discussed such Docker components as Docker client, Docker server, that is actually a set of different processes that are running at Docker host. And Docker host is actually used for creation of those processes and creation of different containers. On Mac OS and Windows, Docker host is virtual Linux machine that is running on Mac OS or Windows computer. On Linux computers, Linux computer is directly Docker host. Let's now proceed, and next let's discuss what is Docker image and what is Docker container. And first, let me describe you what is Docker image. In simple words, I can say that Docker image is simply set of read-only files. That's all. And based on the image, you are able to create container or different containers. Let's first have a look at list of images that are already present on my computer. If I enter docker images command, I'll see list of images that are present in local cache on this computer, and those images were downloaded from Docker Hub. Every image is just set of files, but talking more correctly, it is set of file system layers. We will get back to it pretty soon. For now, just understand that every image is read-only set of files that is used for creation of containers. That's all. In this list, you see actually images that were created already by someone else. But you are also able to create your custom images and reuse them for creation of containers. But what is container? Let me explain you that in the next lecture. I'll see you just in a bit. Bye-bye. Docker image is simply set of file system layers, or in simple words, set of files. You are not able to modify those files, you are able to only read them. If you want to create new image based on other image, you could of course do that and add additional file system layers or additional files on top of existing Docker image. But Docker images are actually used for creation of containers. And picture is like this. From single Docker image, you are able to create multiple containers. And again, quantity of containers that you could create from the same image depends only on amount of resources you have on your Docker host. That's all. Alright, let me quickly demonstrate you how you are able to create containers from specific Docker image. For that, you could use command docker run. And let me quickly create container based on busybox Docker image. Docker run busybox. And here I'll add -it options. And new container was created. I am inside of it. And if I'll have a look at containers that are currently running using docker ps command, you'll see that there is now single busybox container. I could create one more container using same command, docker run -it busybox, and let me run it in background as well, like this. And if I'll list containers now, I'll see two different containers that are running at the moment, but image is the same. It is busybox. And that proves that you are able to create multiple containers from the same image. And actually every container has so-called writable layer. And that means that now you are able to modify container that is running. For example, you are able to create new file inside of the container. Let me do that here in this busybox container. Touch file.txt. And if I list files now here, you will see file.txt on the list. And again, that's because containers are writable. You are able to create and modify files inside of container. Great, that's what is container in short words, and next let me explain you what is Docker Registry and what is Docker repository. I'll see you in the next lecture. Bye-bye. You know now what is Docker image and what is Docker container, and you are able to create multiple containers from the same Docker image. And difference between Docker image and Docker container is that you are not able to modify Docker image, you are able only to read it, or create other image on top of that image. Also, when you create container, Docker creates writable layer and you are able to modify or create new files inside of the running container. And I have just shown you that you are able to launch multiple containers based on the same image. Now let me explain you what is Docker repository. Probably you know what is Git repository. If you don't know, please check out my large course called Complete Git and GitHub Guide, where I explain all details of Git and GitHub. But in short words, Git repository is simply set of files, and you are able using Git to track changes in repository. You are also able to publish your Git repository to hosting service, like GitHub, for example, or Bitbucket. And that is Git repository. What is Docker repository? You are able to create Docker repository from Docker images. And in every Docker repository, you can have different versions of Docker image. And you are able to create different versions of specific Docker image using tags. By default, every Docker image should have at least single tag called latest, but you are able to assign different tags to different versions of Docker images. And this set of Docker images with different tags is called Docker repository. That's it. For example, if I'll go to list of images here on this computer, let me exit from this busybox container and enter Docker images command, I'll see such containers, for example, as WordPress. And you'll see two such kind of containers with two different tags, 5.4 and latest. And that means that actually those two different images belong to same repository. But they were downloaded from Docker Hub. That is actually repository hosting service called Docker Registry. And let's discuss what is Docker Registry in the next lecture. I'll see you just in a moment. Bye-bye. Now you know that Docker repository is actually a set of different versions of Docker image. And you are able to create different versions of Docker image using Docker tags. You are able to assign multiple tags to the same Docker image. And of course, you are able to create custom images on your local computer. But what if you have created really awesome images and you want to share this work with others? You could, of course, transfer those images via email or any FTP service or something else, but usually if you want to exchange your work with others, you should use registries. And the very popular registry is, of course, Docker Hub. You are able to create repositories there and make those repositories available for others. Let me actually demonstrate you how that works. Let me go here and first let me explain you what is registry. Registry is actually just a set of named Docker images. And of course, you are able to create even your local registry with set of images. But of course, no one will be able to pull those images from your computer. And if you want to share your work, you could use public registries like Docker Hub. It is cloud-based images registry service. And the Docker Hub, you are able to create either public repositories available for everyone or private repositories available only to members of your company, your organization. Let me go to Docker Hub and show you how it is structured. It is located at hub.docker.com. If you scroll down here, you'll see a set of popular official images. For example, if I'll click at the Redis image, you'll get to the page of this specific image, Redis. It is official image. And if I'll scroll down, you'll see different tags that you are able to use with this image. And that means that there are at least 5 different versions available in this Docker repository. And you see that multiple tags may be assigned to the same image. And it has tags 601, 60, latest, and so on. And you are able to pull this image, actually everyone is able to pull it from Docker Hub and use it locally. And basically process is following. Let me show you it here. When you pull images from remote repository, Docker actually downloads them to your local computer, and they are available afterwards in your local cache. And actually, I have shown you my local cache on this computer that holds already large set of images like WordPress, PHPMyAdmin and so on, because I have already pulled those images before. And if you want to reuse those images locally, you could of course store them at your local computer. But if you don't need them anymore, you could safely remove them and pull them afterwards again from Docker Hub if you need to. Again, Docker Hub is very similar to GitHub, that actually also hosts Git repositories, and at GitHub you are able to pull different repositories that are public. You could make changes in them, you could push changes and so on. Similarly, Docker Hub works. It is registry that holds different Docker repositories. That's all for this lecture, and next let me summarize what we have discussed in the previous lectures and how different Docker components interact with each other. I'll see you in the next lecture. Bye-bye. We have just discussed the most important components of Docker, and now let me quickly explain you how those components interact with each other using this diagram. Here on this diagram you see Docker client, and on Docker client you could issue different commands like docker pull, docker images and so on. I have demonstrated you some of those commands in the previous lectures. Also next there is Docker server that actually has multiple processes running. And Docker client communicates basically with Docker daemon, and Docker daemon waits for commands from Docker client. And afterwards, Docker daemon interacts with other processes. For example, it could interact with container D process that will create new container based on specific image. There is a set of images available locally at Docker server called local cache. If specific image you want to use for creation of container is not available in local cache, then Docker daemon goes to remote registry, for example, Docker Hub, finds specific image in that remote registry and downloads it to local cache. And only afterwards it creates new container based on that downloaded image. That's how Docker client interacts with Docker server, and how Docker server, specifically Docker daemon, interacts with remote registry or creates new containers based on images located already here in local cache. Also, under the hood, there are a lot of other actions that happen when every new container is created. For example, every container gets its own IP address. Also, new file system layer is created for every container. Also, new processes are started for every container. Every container has at least one process. And all of that is managed by Docker engine, by multiple processes actually that are running inside of Docker host. That's all, guys, for this overview of different components of Docker, like Docker client, Docker host, Docker server, and so on. I hope you enjoyed this set of lectures. In this section, we will start some practice activities, and I would like to start with explanation of list of commands that you are able to use in Docker. And there are two different blocks of commands, called management commands and commands. Historically, before in Docker, there were only commands. But as you see here on this diagram, list of commands is very large. And as soon as the list of Docker commands became very large, Docker developers have decided to split those commands into management commands. And now there are several management commands available, like container, context, image, network, node, plugin, and so on. And basically, along with management commands, you are able to use additional commands. It means that management commands require additional commands as arguments. Let me now quickly go to terminal and show you those commands in practice. Docker, and you should get the list of all available commands with short descriptions. And if you scroll up to the beginning of this output, you'll see management commands block. For example, using image management command, you are able to manage images. Using secret command, you are able to manage Docker secrets. Using volume management command, you are able to manage volumes. Also below you'll see list of commands, and those commands basically don't require additional arguments, but some of them have available options and you are able to supply some additional arguments as options. For example, there are such kind of commands as exec, export images. With images command you are able to list images that exist in your local cache. With, for example, ps command you are able to list containers that are currently running. That's commands that you could use. Alright, next let me explain you how you are able to get help about specific command. Let me clear terminal, Command K, and here type docker ps-help. ps is a regular command, it is not a management command. And let's press enter. And here in this output you'll see which options you are able to use along with docker ps command. There are short versions of every option like -a, and there are also long versions of every option like --all. And if some long options have available shortcuts, then they will be listed on the same line, like this option, -a or --all. And with this option you're able, for example, to show all containers, including stubs containers. In the same way, you are able to get help about management commands. For example, if I'll type docker container --help. And in this output, you'll see list of available sub-commands that you are able to use along with docker container management command, like attach, commit, cp, create, diff, and so on. If you want to get help about specific command for management command, you need to type this sub-command after management command, like this, docker container. Let's say I want to get help about wait command. Wait, and next I'll add option --help. And here in this output you'll see basically help for this specific command that you could use along with this container management command. And you see that this wait command will block until one or more containers stop, then print their exit codes. Also, let's have a look at the help, for example, for rm command. Docker container rm --help. And you'll see that this subcommand has basically some additional available options, like -f or -force -l or -link and -v or -volumes. Alright, that's how you're able to get help about Docker commands and Docker management commands. But basically some of Docker commands are redundant to Docker management commands. And let me talk about that in the next lecture. I'll see you then. Bye-bye. Alright guys, in the previous lecture I have explained you differences between Docker commands and Docker management commands. And Docker management commands have appeared not long ago, and they actually combine some of regular commands. And some people say that you must use only management commands and forget about commands. But I will argue with that because Docker commands are much shorter and they are much quicker to type. And also please note that you don't need to remember all those commands listed here. You will use just a part of them on regular basis. Alright, in this lecture I want to show you some alternative versions of some popular commands that you could use either with commands or management commands. And here is such list. For example, most popular command is docker ps, and this command lists all containers that are currently running. And alternative version for this command with management command is docker container ls. And of course, this command has more characters and you need more time to type. That's why I prefer personally to use this shortcut docker ps. Next alternative pair is docker build and docker builder build. And with this command you are able to build new image. And again, please note that those commands are completely equivalent and you are able to use either this one or this one. Great, next pair is docker inspect and docker container inspect. With this command you are able to inspect and to read details about specific container that was created before. And again, you're able to use either shortcut docker inspect or docker container inspect, where container is management command and inspect is sub command. Next example is docker commit and docker container commit. With this command, you're able to create the image based on specific container. And the last example is docker run and docker container run. It is also a very popular command, and I prefer to use this shortcut. With this command, you're able to start a new container. Or if you want, you're able to use management command docker container run to perform the same action. Great, that's our alternative of some commands, and much more commands have alternatives with management commands, but I have just shown you some examples of them in order to get an idea of what is alternative command for management command. Great, let me quickly go to terminal and use docker ps command. And this command will show you currently running containers. And at the moment, this list in my case is empty. And I could use same command with management command docker container ls, and here in this output you see same result as you see in docker ps output. And that means that those two commands are completely equivalent. Great, that's all for this lecture, and please note that you're able to use either short versions of commands or long versions with management commands. And probably in the future, Docker developers will remove some Docker commands like docker ps, docker build, docker inspect, but I personally don't think so, because many people use short versions and they are used to them. Alright, let's proceed, and next let's start talking about containers and images and start performing some practical activities, and I'll tell you how to pull image from Docker Hub and how to create new container based on that image. Also, I'll explain you structure of image and container. I'll see you in the next lecture. Bye-bye. Alright, in the previous lecture I have explained you differences between management commands and commands. And you know that there are pairs of commands that are called alternative commands, and you are able to use either alternative short command or long command with management command. For example, docker ps and docker container ls is pair of alternative commands. Alright, let's now proceed, and I'll tell you now about most popular commands that are used for containers management in Docker. First command, docker run, is short version of command docker container run. This command starts new container. And you are able to create multiple containers simultaneously on the same Docker computer. Next command, docker stop. This command stops running container. And when this command is executed, Docker basically sends under the hood a sig-term signal to specific process inside of the container. And if that process reacts to sig-term command, then container will be stopped pretty fast. But sometimes processes don't react to sig-term signal, and in such case, after entering Docker stop command, you'll need to wait 10 seconds, and afterwards Docker will fall back to docker kill command. And this command actually sends sig kill signal to specific process, and the corresponding container terminates very fast. Alright, next command is docker rm. With this command you are able to remove specific container that was already stopped. You are not able to remove a running container. You need to stop it first and only afterwards remove with docker rm command. Next command, docker ps lists running containers. And this command is already familiar to you, and I have used it in a previous lecture. Alternative long version is docker container ls. And last command is docker ps-a. With -a option supplied to ps command, you are able to list all containers, including stopped containers. Please notice that instead of -a option, you are able to use also long version of this option --all. That's all for most popular container management commands. And next, let me briefly overview most popular images commands. Docker pull command is used for pulling image from Docker Hub. And if corresponding image already exists in your local cache, then no pull will be performed and you will be able simply reuse currently located in your local cache image. Next command, docker images lists downloaded images that were already downloaded, pulled from Docker Hub to your local cache. Docker RMI removes image or images from your local cache. If you don't need some images, you could simply use this command in order to free up some space on your local setup. And finally, example of additional commands that you could use along with images is docker build dot. With this command, you are able to create new custom image based on created Docker file. Great, that's all for most popular commands that are used for management of images, for pulling images, listing images, and removing images. And next, let's start some practice activities, and let's pull first image from Docker Hub and create container based on that image. I'll see you in the next lecture. Bye-bye. Before going on, I need to perform some cleanup of my Docker setup, because I have some cached images and some containers that were stopped. If you have clean Docker setup, feel free to skip this lecture and move on to next one. Alright, let me list containers here that were stopped, docker ps-a. And here I see a bunch of stopped containers. And in order to remove all stopped containers, I could use command docker container prune. There is no short version of this command, that's why I'm using container management command along with prune subcommand. Type yes here, and all stopped containers were deleted. And now if I list containers using same command, docker ps-a, I will not see any containers on the list. Great. Let me now list all images that I have before pulled from Docker Hub. For that I could use short command docker images. And here is long list of images that I have used before in the previous long practice chapter. And I see such images as MySQL, WordPress, HTTPD, Redis, and so on. At the moment, those images are not used and there are no containers created from those images. That's why I am able to safely prune those images. And for that, I could use docker image prune command. Let me first list all commands, subcommands of docker image management command, docker image --help. And here is this list of subcommands that you are able to use along with image management command. And here is prune command, and with help of this command, you are able to remove unused images. Image is considered unused when there are no running or stopped containers that were created from this image. Great, let me now list all possible options for prune command. Docker image prune --help. And here are some options. And notice that with -a option or --all, it is long version of this short command, you are able to remove all unused images, not just dangling ones. It means that just with docker image prune command, Docker will remove only so-called dangling images. And image is considered dangling when there is no corresponding version of this image at Docker Hub. For example, when you have pulled specific image from Docker Hub, but afterwards such image was removed from Docker Hub, but it remains in your local cache. This image is called dangling image. But I want to remove all unused images, and that's why I need to add -a option to docker image prune command. Let's do that. Docker image prune -a. Yes. Notice that this will remove all images without at least one container associated to them. At the moment I don't have any containers running or stopped. Great, let's press enter here. I need to cut out because Docker is removing several gigabytes of images. And finally images were deleted. And in this output I see a long list of logs, like deleted SHA-256, and then comes a list of hexadecimal characters. And here in this output I see a long list of such logs. Also I see such logs as untagged node latest or untagged node at SHA-256, and then comes again SHA-hash. And again, this list is much longer than amount of images I have used on this Docker machine. And the reason for that is that basically every image consists of multiple file system layers. And that's why Docker has removed corresponding file system layers instead of just removing images. That's why in this log output I see multiple lines, because every image may have multiple FS layers. For example, this BusyBox image had 2 layers, that's why here I see those 2 deleted lines. Alpine image has only one, that's why here I see only this one deleted line. But no worries, we will talk about all those details a bit later. For now, you need to understand that I have successfully deleted all images that were stored in my local cache. And now if I'll enter docker images command, I'll see nothing. There are no images in my local cache and we are able to go on. Next, I'll start from scratch and download very first most simple Hello World container and explain you what happens under the hood and what is the structure of that image that we will download. I'll see you in the next lecture. Bye-bye. Alright guys, let's now start from scratch and let's download the first image from Docker Hub. Recap that Docker Hub is a Docker registry that hosts Docker repositories. And the Docker repository is a set of images with different versions. Alright, we will use docker pull command in order to download image from Docker Hub. Please note that there is alternative version for this command with management command, that is docker image pull. And first let's open up Docker Hub page and let's find here image called Hello World. Type Hello World and here is this image on the list. Please click on it. On this page you'll see details about this image and here is command that you are able to use in order to pull this image from Docker Hub to your local cache. Notice that this is the most simple image available and basically it is useless and all what it does, it simply prints block of text to terminal, that's all. Alright, let's now use docker pull command in order to pull this Hello World image. Let me go to terminal, verify that at the moment there are no images in my local cache, and now let's use docker pull command and type here name of the image, hello-world, like this. Using default tag latest, pulling from library Hello World, pulling fs layer, pull complete. Here is SHA-256 digest for this particular image and status downloaded newer image for Hello World latest. And now if I'll check images in my local cache, I should see Hello World image on the list. In this output I see repository name Hello World, I see tag latest, image ID, here is this ID. Notice that this ID is a short version of long ID of this image. Next, I see when this image was created, date is 4 months ago, and its size is only 13 kilobytes. It is the most smallest image available. Alright, let's now try to pull another image using same command, docker pull, but probably let's use docker image pull command in order to show you that this command is actually alternative version for docker pull command. Docker image pull, and let's pull, for example, busy box image. It is another popular small image. Let's press enter. Again, same output using default tag latest, pulling from library busybox, pull complete, digest, downloaded newer image for busybox latest. And now if I'll enter docker images command, I'll see 2 images in my local cache. And please notice that size of busybox image is a bit more than 1 megabyte. It is of course larger than Hello World image, but anyway it is really small. That's how we were able to download images from Docker Hub. And please notice that we were not prompted to enter any username or password. And that's because Docker Hub is free for use to anybody and you are able to download official images like busybox, Hello World without any credentials. Alright, that's all for this short lecture where I have shown you how you're able to get images, to pull images from Docker Hub. Next, let me explain you structure of the image and explain you why here we have seen messages like pulling fs layer and afterwards you have seen message pull complete. Let's talk about it in the next lecture. I'll see you there. Bye bye. We have just successfully pulled 2 different images from Docker Hub, and those images are Hello World and busybox. And basically now we are ready to create new containers from those images. But before doing that, let me explain you structure of every image and explain you actually key points about images. In a nutshell, every image is simply set of files. That's that simple. And when you pull image from remote registry like Docker Hub, you download simply a set of files and folders. That's that simple. But every image is actually splitted into different file system layers, or shortly FS layers. And you may ask me, what is the reason for splitting images into multiple FS layers? Answer is very simple. Using such splitting approach, we are able to reuse different FS layers in different images. For example, let's say that there is an image that has PHP installed in it. And now you want to create image that will be running WordPress. You probably know that WordPress uses PHP. And if you create WordPress image, you could reuse FS layers in the PHP image and add additional layers that will install WordPress and run it afterwards. That's reusability of different FS layers. Also, every image has so-called base image. For example, base image could be BusyBox, or Alpine, or Ubuntu, or something else. And on top of that base image, you are able to add additional layers, like in this example, layer 1, then on top of layer 1 you add additional layer 2 image, and next you'll add additional layer 3 image. And different images may have different quantity of FS layers. Some simple images may have just 1 or 2 FS layers. More complicated images may have tens of different layers. Alright, let me now talk about key points about Docker image. First of all, Docker image is read-only. You are not able to modify existing Docker image. It is not possible at all. But you are able to create custom image based on other image, if you want. And if we'll get back to images that we have already pulled from Docker Hub, Hello World and BusyBox, you are not able to modify those images. You are able just to create containers based on those images, or create other images based on those images. Next, as I have already told you, every image consists of multiple file system layers. And there could be 1, 2, 3, tens, hundreds of different FS layers, as much as you want. Next, images could be stored in a private or public repositories. And we have actually used public repositories for Hello World and BusyBox images. And those repositories are available at Docker Hub public registry. But you're also able to create private repositories if you create some proprietary images and that your company only uses. Next, images could be copied, deleted, or moved. And actually, in the previous lecture, we have simply copied images from a remote server to our local computer. And in the same way, you are able to copy images from your computer and move it to other computer if you want to. Because every image, again, is simply a set of files. But during the download process, you may have noticed that we were pulling different FS layers. And actually, when you pull image from remote repository, from remote registry, then you are pulling archived FS layers. And if, for example, image has 3 different FS layers, then you'll download 3 different archives. It is done for optimization of bandwidth usage. And afterwards, on your local computer, Docker will extract contents from those archives. Alright, next you are able to use official or community images. And in the previous lecture, Hello World and BusyBox images were official images. And if I'll go back to Docker Hub, here you'll see that Hello World is Docker official image. But if I'll type, for example, let's say PHP, you'll see that there is also PHP official image available. But if I'll scroll a bit down, you'll see such images as phpMyAdmin / phpMyAdmin, php docker.io / php73 fpm, and those images are community images. They were created by specific users. This image was created by phpMyAdmin user, this by PHP. Now you know that every image is read-only and it has multiple FS layers. Now it's a good time to create new container based on already pulled image. And let's create first hello world container. For that, let's use docker run command that will create new container, and afterwards, as argument, we supply name of the image we want to use, hello-world. Recap that this image is already located in our local cache. We have already pulled it from Docker Hub. Great, let's press enter. And you simply see some text in this output, and afterwards we got back to terminal. And that means that container is no longer running. It has performed some job and that's it. And now there are two questions. First one, why this container has printed this text to the terminal? How it knows which action to perform when we create new container? And second question, why this container has exited? Why it is no longer running? Actually, I could verify that it is not running anymore using docker ps command, and list of active containers is empty. Before answering those questions, let me read together with you this output. Hello from Docker, this message shows that your installation appears to be working correctly. To generate this message, Docker took following steps. First step, Docker client contacted the Docker daemon. Recap that Docker command is actually Docker client. It is a binary file located at your computer. And when you enter Docker along with any additional commands, Docker client contacts Docker daemon and sends this command to it. That's what happened under the hood. Next step, Docker daemon pulled hello world image from Docker Hub. Basically, we have already pulled this image, that's why this step was skipped. Docker has verified that there is already hello world image located in local cache, that's why there is no need to pull it from Docker Hub. Next step, Docker daemon created a new container from that image which runs executable that produces output you are currently reading. That means that Docker has created new container based on hello world image. But what is actually container? I'll answer this question in the next lecture, but let me finish reading this output. Finally, Docker daemon streamed that output to the Docker client, which sent it to your terminal. It means that communication between Docker client and Docker daemon is bidirectional. Docker client sends some commands to Docker daemon, and Docker daemon returns some result. And this result was returned actually by Docker daemon, and Docker client has printed this text to the terminal. And afterwards, last step that was omitted here, this Docker container was stopped, because it has already done its job. Now let me proceed, and next let me clarify a bit deeper what actually happened under the hood and what is container and why container decides to print such text to the terminal. Let me talk about it in the next lecture. Bye-bye. Now you know that every image is read-only and it has multiple FS layers. Now it's a good time to create new container based on already pulled image. And let's create first hello world container. For that, let's use docker run command that will create new container, and afterwards, as argument, we supply name of the image we want to use, hello-world. Recap that this image is already located in our local cache. We have already pulled it from Docker Hub. Great, let's press enter. And you simply see some text in this output, and afterwards we got back to terminal. And that means that container is no longer running. It has performed some job and that's it. And now there are two questions. First one, why this container has printed this text to the terminal? How it knows which action to perform when we create new container? And second question, why this container has exited? Why it is no longer running? Actually, I could verify that it is not running anymore using docker ps command, and list of active containers is empty. Before answering those questions, let me read together with you this output. Hello from Docker, this message shows that your installation appears to be working correctly. To generate this message, Docker took following steps. First step, Docker client contacted the Docker daemon. Recap that Docker command is actually Docker client. It is a binary file located at your computer. And when you enter Docker along with any additional commands, Docker client contacts Docker daemon and sends this command to it. That's what happened under the hood. Next step. Docker daemon pulled hello world image from Docker Hub. Basically, we have already pulled this image, that's why this step was skipped. Docker has verified that there is already hello world image located in local cache, that's why there is no need to pull it from Docker Hub. Next step. Docker daemon created a new container from that image which runs executable that produces output you are currently reading. That means that Docker has created new container based on hello world image. But what is actually container? I'll answer this question in the next lecture, but let me finish reading this output. Finally, Docker daemon streamed that output to the Docker client, which sent it to your terminal. It means that communication between Docker client and Docker daemon is bidirectional. Docker client sends some commands to Docker daemon, and Docker daemon returns some result. And this result was returned actually by Docker daemon, and Docker client has printed this text to the terminal. And afterwards, last step that was omitted here, this Docker container was stopped, because it has already done its job. Now let me proceed, and next let me clarify a bit deeper what actually happened under the hood and what is container and why container decides to print such text to the terminal. Let me talk about it in the next lecture. Bye-bye. In the previous lecture, we have successfully created a new container based on hello world image, and we have seen such output in the terminal. Now let me explain you what actually happened under the hood and why this container has printed this text to the terminal. Let me show you one more diagram with image example. I have told you that every image is simply a set of different FS layers. In one of those layers there are instructions, text instructions, which tell Docker what it needs to do when new container is created based on specific image. For example, let's have a look at this image. In this image there are several FS layers. Base image is Ubuntu. In the next layer there is an application that was installed in separate FS layer. And for example, there is WordPress application. And finally, there is additional FS layer with some text, with some command that tells what container needs to do when it is created. An example of the command in this particular image is start WordPress process. Of course, this command is in human words, but under the hood it will be different. But again, idea is that there is specific command that tells what to do, which process to start when new container is created. And in this example, when we have started hello world container, there is an instruction to run specific executable file that prints text to the terminal. That's it. And I could actually quickly show you where is this file inside of the container. For that I could enter docker inspect command. Actually, I need to enter docker ps-a first in order to find out ID of the container. And next type docker inspect and copy this ID from here, like this. And let me scroll up a bit. And here you could find cmd instruction. And in this container, hello file was executed. It is basically Linux executable file. And its goal just simply print such text to the terminal. That's it. Alright, but what is container? And what you are able to do inside of the container? Let me answer this question in the next lecture. See you there. In the previous lecture, I have explained you what happened when we have created new hello world container from hello world image. And basically, executable file called hello was executed, and the responsibility of this file is simply to print text to the terminal. That's it. And afterwards, container was stopped. Now let me explain you what container actually is. On this diagram you see image layers here. And you already know that every image is read-only. All FS layers in the image are read-only. You are not able to modify them. When you create a new container from a specific image, Docker creates very small writable layer. And you are able to read from that layer and write to that layer, create new files and folders. And every container has its own writable layer. In this example, there are two different containers, container A and container B, created from the same image. Let me quickly do that actually. Let me go to terminal and create one more hello world container, docker run hello world. And I see same result. And if I'll enter docker ps-a command now, I'll see that there are now two different stubs containers. And those two different containers used same hello world image, here and here. But command that was executed inside of every of those containers was the same. It was launch of the hello file. Alright, let's proceed. After creation of the container, Docker actually launches specific process inside of the container. And as long as at least one process is running inside of the container, container is considered as running. But as soon as process ends, container is stopped. Let me explain you all of this using another diagram. On this diagram there is Docker host. It is Linux computer. There is Docker engine installed inside. Also, every Linux machine has Linux kernel and such resources as CPU, RAM, network and hard drive. And let's suppose that we have already pulled some image from Docker Hub. Here is this image located on the hard drive of this Docker host. And this image, let's assume, has two different FS layers, image FS1 and image FS2. And again, those image layers are located on hard drive of this Docker host. When you enter docker run some image command, Docker will create additional writable layer for new container. That is the first action. And this writable layer will be created here on a hard drive of this Docker host. Next, you know that every image has instructions which are executed when new container is created. And in case with hello world image, this command was run hello executable file. And that means that new process on this Docker host is created for particular new container, like this. So new process is created. This process does some job. And afterwards, if this process ends, Docker removes this container from memory. And in such case, when there are no processes running inside of the container, container will be stopped by Docker. But those files, writable FS layer for this container, remains on the hard drive. But if you remove particular stopped container, then Docker, of course, removes this writable FS layer as well. It means that you are able to create multiple containers like so. Create container 1 with additional writable FS layer. But notice that we don't need to create those layers, because those layers are already present on hard drive, and this container will actually reuse those FS layers. Any processes running inside of this container will reuse those FS layers. Alright. Writable FS layer was created, process was launched, and now let's suppose that this process is a long-running process, like database process, or for example, we execute some scripts, perform some long-running actions, and so on. And in such case, when process is running, container is kept running, and there is process in memory of this Docker host. And of course, Linux kernel manages all requests to resources like CPU, RAM, network from this process. All requests come via Linux kernel. Afterwards, when this container is running, let's suppose that you want to create new container using same image. In such case, again, Docker creates new writable FS layer for new container. Those layers remain here. This container 2 will simply reuse those two FS layers. And next, it creates new process for new container. And again, this process communicates with resources like CPU, RAM, network, and hard drive via common Linux kernel. Container 1 and container 2 communicate via common Linux kernel. But processes are completely independent. They are different, but running on the same Docker host. Alright, that's what happens when you create new containers based on specific image. And key point here is that FS layers of basic image that was used for creation of those containers are reused. They are not copied to any new container. Every new container gets just new writable FS layer. That's it. And when process is stopped in specific container, Docker stops container as well and removes it from memory. But files of this container still remain on the hard drive until you enter docker rm command and remove specific stopped container. As you see from this diagram, Docker utilizes resources of Docker host very efficiently. First, it reuses files on the hard drive. There is no need to copy file system layers from specific image when you create new containers. For every new container, Docker creates just new writable FS layer. All remaining underlying FS layers are reused from this image. And next, Docker does not keep a container running if there are no processes running inside of the container. It immediately stops container when there are no processes running. Alright, let's now go to terminal and let's remove containers that we have created before. Basically, picture in our case is like this. There are no containers running, but there are still two containers on hard drive, but those containers are stopped. Let's go to terminal, and here again list containers that were stopped. There are no containers running. And now let's use docker rm command in order to remove stopped container. And let's first remove this container. Let's take its ID and let's remove it like so. And let's remove second container, but let me use alternative version of this command, docker container rm, and you are also able to use randomly generated name in order to perform some actions with container. Let me copy this name and paste here as argument for rm command. And second container was removed as well. And now there are no containers that are currently running or stopped. Great, but I still have image, Docker images, on a list. Hello world image and busybox image. It means that now picture is following. There are no FS layers for containers, but there is still image on hard drive with corresponding FS layers. Basically, there are two different images at the moment. And you are able, of course, remove images as well using docker rmi command. And here you could type either image ID or name of the image in order to remove it. Let's remove busybox image. Delete it, and let's remove hello world image. Hello world. Hello world image was removed as well. And now if I'll have a look at list of images, I'll see empty list. And that means that at the moment there are no images on hard drive on local Docker host. That's how picture looks like at the moment. Let's continue our Docker journey. Over the course of the previous lectures, we discussed some theoretical stuff and we discussed what is image, what is container, and you already know that image is basically read-only and it consists of multiple layers. And when you run new container based on specific image, Docker creates thin writable layer and multiple containers could be created based on just a single image. And before, we created containers based on such images as Hello World and busybox. In those containers, there were no open ports, and there was no need to connect to those containers from the outside world. But in many cases, for example, web applications or other applications running inside of the containers require external connections. For example, if you create a Node.js Express web server and run it inside of the container, you probably need to connect to it using web interface, and you want to make connection from your web browser on your computer. And in such case, you have to utilize such feature as port mapping. And we will talk about this feature in this lecture. So what is that? Port mapping allows you to connect to applications, to processes actually, inside of the containers using port mapping. In this diagram, you see that there are such containers as container 1, container 2, and container 3. And in each container, there is specific application. For example, in this container, there is application that listens at port 80. But this port is container's internal port. This is very important. It is port inside of the container. And if you just run container like we did before using docker run command, you will not be able to connect to this application from the outside, like that, because this port is just port inside of the container. This is very, very important to understand. Also here on this diagram you see other containers with other applications. For example, here in this container there is another application, and this application listens at port 3000. In this container there is one more application, and it has port 443 opened. But in all three cases, in all those containers, it is not possible to connect to them from the outside world, even from your computer, if you're using Mac OS or PC. So, using port mapping, you could create pairs of ports, like you see here. So first comes host port and next comes container port. And you are able to map host port, specific host port. For example, here you see such port, 8080. And you could map such host port to port of the container. And in this example, container's port is 80. And in such case, by opening, for example, connection in the web browser, if it is a web application inside of the container, and specifying port 8080, you will be able now to connect to application inside of the container 1. That's how it works. So, in port mapping, first port is host port, and second port is port inside of the container. In the same way, you could open connections to, for example, container 2. And in such case, you have to map, for example, port 3000 on your computer to port 3000 inside of the container. Yes, you could utilize even same ports. But main idea is that those ports must be free on the host or on your computer. It means that you are not able to utilize same port, for example, 3000 twice for two different ports mapping. It is also important to mention that ports mapping works a bit differently depending on how you actually run Docker. From the previous lectures, you know that you could run Docker using Docker Desktop if you are either PC or Mac user. So here is this option, PC or Mac. And in this case, you basically create a small virtual machine, and inside of that virtual machine, you run all containers. If you're a Linux user, you basically install Docker engine. And in such case, you actually create Docker host directly on your computer. So, if you are a user of the PC or Mac, then Docker host will be Linux virtual machine. If you are already using Linux, then Docker host will be directly your computer. And if you create port mapping and run, for example, such container as you see here, so container 1, and it has port 80 open, and you create port mapping from port 8080 to port 80, Then, if you are running Docker desktop, you will be able to connect to this application A inside of the container 1 by opening web browser and launching connection to port 8080 on your computer, not inside of the Linux virtual machine. Docker will do this proxying of the ports from your computer, PC or Mac, to the port inside of the container. If you are a Linux user and you have installed Docker Engine, then behavior is the same. But there is basically no separate Linux virtual machine. Your computer is Docker host. And on this Docker host, if you open, for example, web browser and connect again to port 8080, you will land inside of the container, and Docker will proxy such connections to internal port 80 inside of the container. So that's how it works. Using ports mapping, you could provide basically external access to any application inside of the container. And as we already discussed, each container is usually single-purposed, and usually just a single application is running inside of the container. And therefore, usually only single port is opened inside of the container. But for example, if you run some kind of database inside of the container, for example, MongoDB or MySQL, then you might probably have several ports opened. And if needed, you could actually create ports mapping for multiple ports. Alright, that's theory, and next, after the small pause, let's try that on practice and let's create NGINX container. It is actually a web server, and we will open ports using ports mapping for that container. See you next. Alright guys, we just discussed what is ports mapping, and now let's apply this knowledge in practice. And we will create the first container based on the image which is called NGINX. It is official Docker image, and we will pull it from Docker Hub, because now I have actually clean Docker setup. I have no images and no containers running. I could basically verify that quickly. Docker ps-a, no containers either running or stopped. And if I enter Docker images, I will also see empty list. So, we will first create a container based on the NGINX image, without ports mapping, and we will try to connect to that container running NGINX. And you'll see that this attempt will be unsuccessful, and afterwards we will try to create ports mapping and run container once again, and afterwards connection will be successful. So, let's start with that. Let's first use docker run command in order to create container based on the image called NGINX. We will not specify any tag. In such case, Docker will download the image with latest tag. So let's run such container in detached mode. Let's add -d option, and here will be name of the image we want to utilize for this particular container, NGINX. Unable to find image NGINX :latest. Latest here is tag. And now you see that Docker is pulling image from the library. It is basically pulling it from Docker Hub. Pull complete. And here is SHA-hash of the downloaded image. And if I enter command docker images, I'll see that there is now image called NGINX with tag latest. Here is image ID, and it was created several days ago, and its size is 141 megabytes. Alright, now I should have NGINX container up and running. Let's verify that as well. Docker ps. And here is such container. Here is its container ID. Here is image which was utilized for this particular container. Here is command that was executed in order to start actual container. Created 30 seconds ago, up 31 seconds ago. And here is randomly chosen name for this particular container. And in order to perform different actions with such container, you could utilize either container ID, this one, or container name. So it doesn't matter what you will utilize. Now let's do following. Let's try to examine which port is actually opened inside of this container. For that, we could utilize command docker inspect, and it requires an argument, either container ID or container name. Let me take container name. In your case, container name will be completely different, because again, they are randomly generated. And of course, container ID in your case will be different as well. So let's docker inspect, and here paste either ID of the container or name. So I'll paste actually ID. So let's inspect such container, and you'll see all details about this particular container. For example, here I see that such IP address was assigned to the container. And gateway is this one. And this IP address is basically IP address inside of the Linux virtual machine, because I'm running Docker desktop on my Mac. And such IP addresses are assigned to containers dynamically by Docker. And you notice that such gateway and this IP address belong to the same network. Prefix length here is 16 bits. Alright, let's find information which we are interested in, and that is actually port which is opened inside of this container, and here I see this information. Port 80 TCP is opened inside of this running container. And it is actually reasonable, because we are running NGINX, it is web server, and web server is usually running on specific port. And default port for NGINX web server for this particular official NGINX image is 80. But let me now try to connect to this port 80. Let me try, for example, to grab this IP address from here and go to Google Chrome. Let me go there, and here let me paste this IP address. So connection was unsuccessful. This site can't be reached. Reason for that is that by default you are not able to get access to containers by their internal IP addresses, which were assigned to those containers by Docker. So there is no direct connection from my computer to this IP address. Here I clearly see that this site can be reached. So let's now try following. Let's try to connect to localhost instead of this IP address. Localhost. Like that. And again, I see this site can't be reached. And I have just tried to connect to localhost IP address of my primary computer using port 80, because if you don't specify port here, web browser will assume that you want to make connection to port 80. If you want to use other custom port, for example port 443, you could specify it after colon here in the address bar. So let's try that, for example, and I also see this site can be reached. Alright, now we are not able to connect to this web server from our computer. And the reason for that is that we have not published any ports using ports mapping. Recap that command which we utilized in order to run this container is here, docker run -d NGINX. Simple as that. Simply run container based on the image NGINX. And now let's try to create container with ports mapping. And we could either keep this container running or you could stop it. Let me actually stop it, docker ps. Let's stop it using command docker stop, and here you could either specify container ID or container name. Let me take container ID, so docker stop, and let's remove it as well. Docker rm, and here paste again ID of the container. Now I don't have any containers, docker ps-a. And now let's create container based on the same image NGINX with ports mapping. Docker run. Next will be same option as before, -d, run in detached mode. And also let's add here one more option, -p, that stands for publish. And let's publish internal port 80 of the container to port, let's say, 8080 on our computers. Similarly as we discussed here on this diagram. So internally there is port 80 open inside of the container, And external mapped port will be, for example, 8080. You could choose any port you like. One single requirement here is that such port must be available, must be free on your computer, either PC or Mac if you're using Docker desktop, or on your Docker host directly if you use Docker engine. So I'll choose port 8080. So first comes external port, and after colon comes internal port inside of the container, 80, like that. So our NGINX web server is running at port 80. And afterwards, same as before, let's specify name of the image we would like to utilize for this particular container, and it is NGINX. Let's run such container, and here I see following error. Error, response from daemon, ports are not available. Listen TCP for zeros 8080, bind address already in use. And it seems that on my computer, this port is already occupied by some other application. And that's why I was not able to run this container using such ports mapping. In your case, probably this attempt was successful if port 8080 is open on your computer. Let me try another port, for example, port 8081. Internal port I'll keep unmodified. Let's try that. And now I see that container was successfully created. And here is full SHA hash for this particular container. Let's verify that container is running, docker ps. And yes, here is this container. By the way, here you see just part of this hash, so few first characters. Full hash is here. You see it when you create specific container using docker run command. Image is NGINX. Command is here same as before, created and status. And here now I see ports mapping. Here I see 4 zeros, and it means that I will be able to access internal containers application using any of my ports on my computer, either localhost or IP addresses assigned to my network interface cards on my computer. And here is actual ports mapping. Port 8081 on my computer is mapped by Docker to internal port 80 inside of the container. And such mapping was created only for TCP. UDP connections will not be allowed for such ports mapping. So only TCP connections are allowed. And here is randomly assigned name for this particular container. Let's now try to open connection to this NGINX container. And I will utilize port 8081, and you should utilize that port which you used in order to create container. If port 8080 is open on your computer, then please open connection to port 8080. Let's go to web browser, and here I'll enter in address bar localhost colon 8081, because that is that port which I utilized for ports mapping. So localhost 8081. And I see welcome to NGINX. It means that now I am able to connect to application inside of the container by using external port on my primary computer. Also, I can utilize, instead of localhost, IP address 127.0.0.1, like that, and connection will be successful same as before. Welcome to NGINX. By the way, this actual HTML page is located inside of the container, and it is served by container. Alright, that's how you could enable ports mapping for a particular container. For that, you should utilize option -p, which stands for publish. And single requirement here is that such port which you open on your main computer for connections to container must be available for use. And in my case, such port was not available, and that's why I just utilized another port, port 8081. Alright, that's it for ports mapping, and in similar way you could open connections to any applications inside of your containers. And now let's stop this container, docker stop, and let me take ID of this container. stopping, and let's remove it as well. Docker rm, and here is ID of this container. Alright, I removed this container, and that's basically it for this lecture. And in the next one, I'll explain to you what is environment variable and how you could set environment variables by using option -e when you run specific container. And of course, we will explore that on practice, and we will create simple Node.js container and feed specific environment variable to it. I'll see you guys in the next lecture. When you run, for example, front-end or back-end application, or when you create a database, then you, in most cases, need to set some values for initialization of those applications or databases. And those values could be set by setting environment variables. And environment variables are set when application is actually starting. You are not able to modify environment variables during life cycle of the application. In order to apply new environment variables, you have to restart application. For example, when you create MySQL database, you could set such environment variables as you see here. For example, MySQL user, MySQL password, MySQL root password, and MySQL database. And in this example, you see how to set environment variables using Docker when you create new container using Docker run command. So here you just to have utilized such option as -e, and you might utilize it multiple times, as many times as amount of variables which you want to set, like that. And by the way, if Docker command is very long, you could always split it into multiple lines using backslashes, as you see here in this example, like that. Or you could write just a long one line of command. So that's how environment variables could be set when you run container using Docker run. And syntax here is very simple. Here first comes name of the environment variable. So here it is, MySQL user. Next comes equal sign, and after it comes value for specific environment variable. So in this case, WordPress is value for environment variable called MySQL_user. It's a convention to use uppercase letters with underscores between them when you name environment variables. So that's why here in all those environment variables you see such format. And values depend actually on which values you want to set for particular environment variables for particular application, or for example service like a database service which is running using Docker run command, as you see here on this screen. So now let's try that on practice, and in order to make it simple, I'll create a very basic Node.js container, and afterwards we will set environment variable for this particular container, and we will verify how Node.js could read environment variables. By the way, Node.js is a JavaScript runtime environment, and it is utilized for backend JavaScript applications. And for example, using Node.js Express package, you could very easily create a web server which will accept different sorts of HTTP requests like GET, POST, and so on. But this is out of the scope of this course, and now let's simply try to create a Node.js container and feed to it some environment variables using Docker-E options. So let's go to the terminal here, and first let's create a new container, and for that we will utilize Node.js image. Of course, it will be official image from the Docker Hub. But there are actually different tags available, for example, for such image as Node.js. And the sizes of those images are different. If you want to pull the smallest image available, you should utilize tag called Alpine. Let's go ahead and pull now Node.js image from Docker Hub, and we will set tag Alpine for it. So let's use Docker run command which will actually create a new container based on specific image, and if image is absent, it will be downloaded from Docker Hub. So let's run container in detached mode, and we will utilize such image as node, and after colon let's specify a tag alpine, and let's create such container. Unable to find image node alpine locally, pulling from library/node. Again, this image is smallest Node.js image available at Docker Hub. Image was downloaded. Let's list images here, Docker images, and now there are two images on the list, NGINX and Node, and notice size of this Node image, it is 170 megabytes, and tag here is alpine. Here is image ID, and this particular image was updated at Docker Hub 2 days ago. Alright, container should now be running. Let's verify that. Docker ps. Actually, I don't see any container, and the reason for that is that the container was created and immediately exited. In order to keep it running, there should be at least one process, and we have not specified which process we want to start actually inside of the container. Let's do following. Let's first check that such a container was actually launched and afterwards stopped, docker ps-a, and yes, here is such container. It was based on image node colon alpine, and it was exited about a minute ago. Let's run again new container based on the same image using same command as before, docker run -d node alpine, but now let's also add options -it, interactive and terminal. Let's run container in such way. Container was created, and now let's check whether it is available or not. And now I see that this container is up 5 seconds. And let's now go inside of this container by opening SHA shell, which is available inside of the container. Basically, we will create additional process inside of the container. For that, please grab container ID or container name. Let me grab container ID, this one, and enter following command. Docker exec -it, next comes ID of the container, and after space, please specify sh, like that. That stands for SHA shell. This SHA shell, again, is available inside of the Node.js container. So let's run this command, and now I'm inside of the container. And inside of this Node.js container, there is Node executable available. If I enter node -- version, I should see answer in this command line. And here is version of Node.js installed inside of the container. It is version 17.1.0. It is version available in this Alpine image in my case. In your case, you probably will see more recent version of Node, but it doesn't matter. What does matter is that Node.js executable is available inside of the container. And our topic is actually environment variables. And now question, how could we read environment variables using Node.js? We could launch interactive Node.js interpreter. For that, let's simply enter command node inside of the container. We are doing that inside of the container, node. And I see welcome to Node.js prompt. And now here inside, you could basically enter any JavaScript command which will be interpreted by Node.js interpreter. And we are interested in environment variables, therefore, let's try to enter following. Simply process.env. In Node.js, there is special variable called process. It is an object, and it has also property called env. We access such property using dot notation. And this object holds actually all environment variables which were set at the moment when this Node.js interpreter was launched. If I try to access process.env now, I'll see such list of environment variables. And notice that naming convention is here the same as we discussed on this slide, so uppercase letters with underscores between them. For example, node_version or yarn_version. Also, there are single word variables like home, term or path. And those environment variables were set automatically. And for example, here we see that the hostname matches with container ID, where we actually run this Node.js. And now let's try to inject additional environment variables to this container. Actually, not this container, we will create a brand new container for that. Let's exit from Node.js interactive shell, and for that please enter Ctrl+C twice, like that. Now I am back to SHA shell inside of the container. Let's exit out of it as well. And now I am back to my command prompt. If I enter docker ps-a now, I'll see that this container is still up and running. Let's stop it. Docker stop, and here let's use container ID from here, like that. Stop in container. Container was stopped, and if I enter docker ps now, I will not see any containers running. And now let's create again Node.js container with the same command as we used before. Docker run -d-id node::alpine, and let's add here also -e option, like that, and specify environment variable in the format name of the variable =value. And let's, for example, name this variable my_test env, like that. After that comes =, and here will be value, and I'll set value to my name, for example, like that. If you want, you could also chain other environment variables using same syntax. -e, next comes key, =value. But I'll keep only one environment variable in place like that. So let's run new container. Container was created, and now let's try to perform same task as before, go inside of that container, and afterwards launch node interpreter and try to access process.env. And we should see such environment variable there inside of the container. So let's docker exec -it, here will be SHA hash of the container. I could grab just part of this SHA hash like that, and here enter sh. We are opening SHA shell inside of the container. And now let's enter node command here inside of the container. Again, I see welcome prompt. And now let's try to access process.env. And now here in this object, I see my test_env with corresponding value Bogdan. It is string. By the way, all values which you set as environment variables using the -e option are treated actually as strings. And if you want to have such values as numbers, you have to convert strings to numbers by specific application which is running inside of the container. But the main outcome here is that in such case, I am able to access my test_env variable, which was set here using -e option. So here is key name, =, here is value. Alright, that's it for environment variables, and different containers usually require different environment variables, and for example, if you run database, you have to set some database-specific environment variables like you see here in this example. That's it for this lecture, and in the next one, let's talk about volumes. Using volumes, you could map volume, it is actually folder on your computer, to specific folder inside of the container. Let's talk about that in the next lecture. You already know such important concepts as port mapping and setting environment variables. And now it's time to move on to one more important concept in Docker, and that is volumes mapping. Recap that we launched before NGINX container, and we connected to it using port mapping from our local computer. And we saw basically this web page, welcome to NGINX. And this is basically default HTML page located inside of the NGINX image. And it is being served by default by container created from the NGINX image. But question, is it possible to modify this HTML page inside of the container? And yes, it is possible using volumes mapping. So what is volumes mapping? Let's have a look at this diagram where there is a Mac or PC. Inside of it there is a Docker host, it is Linux virtual machine. And inside of the Docker host we actually run different containers. Of course, as I mentioned multiple times before, if you run Docker using Docker engine, then a computer running Docker engine is itself Docker host. But let's have a look at more complicated case when you use Docker desktop on the Mac or PC. So let's assume that there is container and inside of it there is specific folder. And it is possible, using volumes mapping feature in Docker, map folder inside of the container to specific folder either on the Docker host, like you see here in this connection, or it is possible to map folder inside of the container to folder on the Mac or PC computer, like you see here on this connection. And in this case, this connection between different folders will be basically bidirectional. And inside of the container, you will actually see contents of the corresponding folder that was mapped to the container. It means that if you map, for example, this folder here and place some files inside of it, then those files will be visible inside of the corresponding map folder inside of the container. And container will be also able to write to this folder. This is very important. So write operations are by default allowed, and container is able to change contents of the mapped volume outside of the container. It is possible, of course, to create read-only volumes, but by default they are read-write. So what is the difference between mapping volumes from Docker host, like you see here, or mapping volumes from your computer, Mac or PC? Difference is following. For example, you develop specific application on your computer, Mac OS or PC, and you want to run such application inside of the Docker. For example, it could be Node.js or Python or any other application. In such case, all application files are located on your computer here, inside of specific folder, which is named according to your project Python, for example, or Node.js. And you want to execute this application, to run it inside of the container. And in such case, you should map folder from your computer to container and use this connection here. Okay? But let's assume that you want to run database inside of the container. For example, MongoDB or MySQL or Redis or Postgres, any database you like. And you know that each time when you create container based on specific image, Docker actually creates brand new container. And if you run a container with MongoDB database inside, for instance, and afterwards insert some records to this database, and they are stored in this container, temporal container. And as soon as you stop this container and remove, all this data is gone. And when you create a new container based on the same image, for example, Mongo image, it will be empty. It will not have any data from the previous containers, because containers don't share their disks actually. And in such case, you might need such connection between container here and folder inside of the Docker host. And in such case, you are able to persist data from the database inside of the container. on the Docker host itself. And any new container, for example, MongoDB container, back to our example, which will be created inside of the Docker host, could be mapped to the same volume on the Docker host. And your data, database data, will be kept untouched, and other containers could be able to continue using this database. In this case, it doesn't make sense to store this volume on your Mac OS or PC computer. It makes much more sense to store this volume inside of the Docker host. And of course, this connection will be also bidirectional, and it is possible to read and write data to this volume inside of the Docker host. And that's what usually such databases as MySQL, MongoDB or others do. They read records and also modify records or create new records inside the database. And that's possible using volumes mapping between Docker host and container. And different containers might reuse same volume inside of the Docker host. Alright, let's get back to this example where we map folder on our Mac OS or PC computer to container. And if you want to map specific folder, you could utilize, for example, this command. Now we are talking about the case when you run container using docker run command, because it's also possible to map volumes using docker compose. But now let's have a look at this example. Using -v option, you could basically specify that you want to map specific volume, like that. And here, before colon, you specify basically path on your local computer. And here is path inside of the container. In this example, you see volumes mapping for the NGINX container. And basically here you see path inside of the container where default HTML page is located. It is actually called index.html, and that's that page which you see here when you connect to NGINX container using web interface. And you could overwrite contents of this folder inside of the container by using volumes mapping. And here in this example, you see actually path to HTML folder located in the current working directory where you actually enter docker run command with -v option. And with such syntax $, curly brace, pwd curly brace, you actually tell Docker that it should replace this variable with path to current working directory. This syntax is actually universal, and it will work on macOS, Linux-like systems, and Windows. On Windows, you have to utilize PowerShell. There is a small note for Windows users, and I'll get back to it a bit later in this lecture. So, using such syntax, you will actually tell Docker that you would like to map HTML folder located in the current working directory to corresponding folder inside of the container. So here is path to corresponding folder inside of the container. And this connection between this folder and this folder will be actually bidirectional. And it will be possible to read this data from this folder, so in this way. And it will be also possible to write data to this folder by container. So this connection is read-write. Alright, that's it for volumes mapping, and that's how you could enable volumes mapping between your Mac OS or PC computer and container. And after the small pause, we will try that on practice, but here is also a note for Windows users. In order to enable such functionality and be able to share volumes between your local computer and containers, you have to enable file sharing in the settings of Docker. Please go to Resources, File Sharing, and check checkboxes here for local drives which you want to make available for containers. Alright guys, that's it for volumes mapping on Docker, and after the small pause, let's try that in action and let's modify default index.html page for NGINX container. See you next. We just discussed a volumes mapping feature in Docker, and honestly it is most oftenly utilized feature in Docker, because usually Docker is used for development of specific applications, and that's why it is necessary to map different volumes. Also, if you run different applications locally during development phase, you probably require some sort of databases, and inside of the database running containers, you want usually to persist data and reuse it when new containers with databases start. And that's where volumes are used. And now it's time to practice with volumes, and we will map local volume from our computer, in my case macOS computer, in your case probably PC, inside of the container. And for that we will get back to the example with NGINX. And here I still see welcome page from NGINX, and it shows me actually default index.html file inside of the NGINX container. And now let's create volumes mapping and map custom index.html file from our local computer to the container, which will be still running based on the NGINX image. Let's go to the terminal. And by the way, here I am still inside of the Node.js container. Let me press Ctrl+C twice and exit out of this Node.js container. And now let's create again NGINX container. But before doing that, let's open up Visual Studio Code, and there we will create custom index.html file. If you don't have VS Code installed, please install it right now. So let me first cd to desktop, and here on the desktop I'll create folder using mk directory command, and let's name it docker-examples, like that. And let me cd to docker examples. And let me open this folder inside of the Visual Studio Code. If you installed VS Code correctly, it should provide you access to code command, and you could open any folder from the terminal by entering command code and dot. If you don't have such command available, please go to Visual Studio Code and open this folder, Docker examples, by going to File and open here, like that. Alright, so this folder was opened in the Visual Studio Code, and now it is empty. Let me create here a new folder by clicking on this icon, and the name of this folder will be NGINX, like that. Inside of this folder, let's create one more folder, and let's name it HTML. Inside of this HTML folder, let's create new file called index.html. For that, please click New File and type name of the file index.html. Simple as that. Now, inside of the Docker examples folder, there is NGINX folder. Inside of it, there is HTML folder, and there inside there is index.html file. In this file, please simply type exclamation mark, and you'll see suggestion exclamation mark emmet abbreviation. Emmet is actually snippet tool, which allows you to use shortcuts in order to create large blocks of code. And here, if you press tab, by the way, emmet is available in VS Code out of the box. So if I press tab now, you'll see that emmet will actually create such HTML file structure for me. It has HTML tag, here is closing HTML tag, here is head section, and here is body section. In the body section, let's add one more tag. It will be h1 tag, and inside of it, let's type, for example, custom NGINX web page. Let's save changes in this file by pressing key combination Command S on Mac or Ctrl S on Windows, like that. And now there is a modified index.html file here inside of the HTML folder. And now let's try to map this file to container running NGINX. Now we have to do following. In order to perform such mapping from your local computer, you have to cd change directory to this HTML folder. It is much more easier to do in the embedded terminal here in the VS Code directly. For that, please open embedded terminal, Ctrl backtick, like that, and you will land in the Docker examples folder. So now here, please cd to NGINX, because we are working with the NGINX example. cd NGINX. And now here inside of the NGINX folder, you have to enter docker run command. Because inside of the docker run command, we will utilize variable pwd, which will actually access current working directory. And here we want to create full path to HTML folder inside of the NGINX folder here, where we actually have index.html file. That's why we changed directory to NGINX. Basically, you could do the same inside of the terminal. For example, if I go to the terminal, I could cd to NGINX and enter corresponding docker run command here. But let me proceed in embedded terminal here in VS Code. So, let me here enter docker run -it. Also, let's run container in detached mode. I could basically add D option right here after T, for example, or DIT, it is most common. And now after those options, let's first expose internal port from the container to outside world. And for that, we will use -p, publish option, which we utilized before, -p, and I'll expose local port 80 inside of the container to, let's say, port 8888 on my computer. So inside there will be port 80, which is opened by default by NGINX process. And afterwards here will be -v option that stands for volume, and we will map volume. Syntax is here, $, curly brace, pwd, closing curly brace, /html, because we want to map HTML folder which is located inside of the NGINX folder, like that. So $, curly brace, pwd, curly brace, /html. Afterwards comes colon, and after colon we specify folder inside of the container. And for NGINX, this path is here, user share NGINX HTML. So let's type it here, user share NGINX HTML. Double check that everything is written correctly, user share NGINX HTML. Yes, I didn't make any mistake. And now we are able to run container, and of course at the end of docker run command we have to specify name of the image we would like to utilize for this particular container. It is NGINX, like that. And to summarize, we will run new container based on the NGINX image. We will run it in detached mode, also in interactive mode, and here T stands for terminal. -p option tells that we want to publish internal port, in our example 80, to external port all 8s, 8888. Afterwards, one more option is specified here, it is -v, which stands for volume. And here we map such path from our local computer to such path inside of the container. And notice that here we're able to utilize variable called pwd, which will be replaced basically by path to NGINX folder. If you want, actually you could type this path manually, but it's more commonly to utilize variable in such path. Alright, let's run such NGINX container. Container was started, here is its SHA hash. Let's verify that this container is running, docker ps. And yes, here is this container. By the way, I still see node container running. Let's keep it running. So here I see ports mapping, but in this output I don't see any details about volumes mapping. But if I enter docker inspect command, I should see those details. Docker inspect, and here paste ID of the NGINX container. Let me scroll a bit up. So here are details about IP address assigned to this container. Now it is 172.17.0.3. Let me scroll a bit up. So here I see which port is open inside of the container, and here I see where this internal port was mapped to on my local computer. So here I see host port all 8s and host IP is all 0s. As I told you before, this means that you are able to connect to this internal port inside of the container by opening connection to any of your IP addresses on your computer, either localhost or any IP address on your network interface cards. Let's scroll up, and here you should find Mounts section. Here it is. In this section, there is source, as specified here, and destination. And you might notice that Docker has replaced that pwd variable with full path to NGINX folder on my computer. And here is full path to HTML folder on my computer. And it is, let's say, connected to this folder inside of the container. User share NGINX HTML. Read-write is true. It means that the container could read from this folder on my local computer, and also it could write to this folder. It means that if specific process inside of the container writes anything to this folder inside of the container, that will be also written to this folder on my computer. That's what read-write actually means. Alright, we inspected this container, and now let's try that in action. Let's go to web browser, and here let me connect to localhost IP address, but port now will be 8888, that port which I specified in the -p publish option. Alright, let's open connection, and I see custom NGINX web page. That's how it works. So here now let me hide the terminal. Now index.html file located in the HTML folder is mapped to the container, and here are contents of this file. Here I see this custom NGINX web page text, which I see right now here. But what if I change contents of this index.html file? For example, custom, let's say, welcome to custom NGINX web page, like that. Save changes. Let's go back to web browser, refresh page here, and I see that changes were immediately reflected. It means that you are able to modify contents of this mapped volume, right? Because HTML folder is actually mapped to folder inside of the container, and container will automatically in real time see those changes. So here we see updated index.html file. But what if I rename simply this file? Let me rename it to index2.html. Let's go here, refresh page, and now I see forbidden, because now NGINX was not able to locate index.html file, and it wasn't able to serve it to web browser. Let's rename it back to index.html page, and here let's refresh. And now I see again, welcome to custom NGINX web page. Alright, using such syntax, we were able to start new container. Let me get back to this command. So here it is. We were able to start a new container based on NGINX image, and we exposed internal port 80 to external port all 8s, and we also added volumes mapping using -v option here. And we mapped such folder on our local computer to corresponding folder inside of the container. And now let's try to run one more NGINX container. And for example, let's modify here port all 8s to 888, for example, 9, like that, keeping previous NGINX container running. So let's run one more container. Container was created, docker ps. Now here are two NGINX containers, here and here, with different ports mapping. Here is port mapping for this container, and here is port mapping for this container. Notice that port inside of the container is the same as 80, because those containers are two completely separated containers, and they have own internal ports. And let's now try to open connection to this port, 888, and here will be 9, like that. So let's open connection, and here I see the same response, welcome to custom NGINX web page, because same volume was mapped to this newly created NGINX container. Alright, that's it for this lecture, and that's it for volumes mapping. We will also cover briefly how to enable volumes mapping using Docker Compose, but that will be a bit later. For now, you should know that it is possible to map volume either from your Mac OS or Windows computer to the container, and it is bidirectional communication channel, and also it is possible to map volume from the Docker host to container in order to, for example, persist data from the database. Also, it's possible to enable read-only access to corresponding folder on your computer or on the Docker host, because by default, such volumes mapping is read-write. So container is able to modify contents of corresponding mapped volume. Alright guys, that's it for volumes mapping, and next we will discuss topic which is related to launching applications inside of the container, and we will create very basic Python application and run it inside of the Docker container using Python interpreter. I'll see you guys next. Alright guys, we already covered such very important Docker features like ports mapping, volumes mapping, and creation of the environment variables for containers. And we launched different containers using docker run command. And we created such containers as NGINX and Node.js. Now it's time to move on and discuss how we could launch actual applications which we develop on our computers inside of the Docker containers, because that is the task which is managed by Docker most often. And now I'll demonstrate to you how to launch Python application inside of the Docker. Let's go to Visual Studio Code and verify here which containers are still up and running. And at the moment I have 3 containers, 2 NGINX containers and 1 Node container. Let's now do following. Let's stop all those running containers and let's remove them. And now I'll demonstrate to you shortcut how to do that, because basically you could take ID of each container and first stop each of those containers and afterwards remove using docker rm command. There is shortcut. Let me show you. Let me first clear terminal, and here let's first enter following command: docker ps -a-q. And if you enter such command, you'll get list of IDs of the containers which are either stopped or running. And now you could feed this list of containers to another docker command using following syntax. Let's first stop those containers. Docker stop, and here will be syntax like that: $, and here will be parentheses, and inside of those parentheses please enter this command which we just tried here: docker ps-a-q, like that. And let's stop all running containers like that. So containers are being stopped. Again, list of those IDs is sent now to docker stop command. Containers were stopped, docker ps, there are no running containers, and now I could remove all stopped containers using similar approach. Let's go back to this command, docker stop, and instead of docker stop, let's write here docker rm. And this will remove all stopped containers. Let's remove them, and containers were removed. Now if I enter docker ps-a, there will be no containers either running or stopped. Alright, now in order to proceed, let's create one more folder here in our Docker examples folder, and the folder name will be, let's say, Python-up. Let's create folder here, new folder, Python-up. Like that. Inside of this folder, please create a file. Let me, by the way, close this index.html. So inside of Python-up folder, let's create new file called main.py. Py is extension for Python files. And notice that VS Code has recognized that it is a Python file. So main.py. And now here in this file, I'll paste following contents. So here is very simple Python application which will ask you in the terminal for input, and you'll see prompt, please enter any positive number. You should enter number. Then Python will convert such input to integer and assign result to variable n. And afterwards there is if-else statement. If the number which you entered is less than 0, then Python will print to the terminal error number must be positive. This is just string. Otherwise, if a number is less than or equal to 0, we will do following. There will be some variable, and this variable will hold at the end of the application sum of all numbers starting from 0 to the number which you enter in the terminal. For example, if you enter number 5, then sum at the end will be 1 plus 2 plus 3 plus 4 plus 5. Here I reassign value of the variable n to new variable called I, and inside of this loop I actually perform sum operation. While I is greater than 0, I add to variable sum I using plus equal operator. And at the end of this loop, I decrement 1 from the value of the variable I until it becomes 0. When it becomes 0, this loop is exited. And at the end, we print to the terminal sum of all positive numbers till the number which we entered here at the beginning of the application, and here finally we show what is the sum actually, using value of the sum variable. So very simple Python application, and this application does not require any external or internal Python modules. So just very simple math application. Let's now save changes in this main.py file, and let's now think how we could actually run this application. Of course, you could run it locally on your computer if you have Python interpreter installed on it. Mac OS computers come with Python pre-installed. It means that if I open up terminal, by the way, let me go out from the NGINX folder because we are done with NGINX example, and let me cd to python-app folder. So here we are. So if I enter here Python 3 -- version, I'll get a version of the Python which is installed on this macOS computer. On macOS there are two different versions of Python pre-installed, Python 3 and Python. That's why if I want to perform some actions using Python 3 interpreter, I should enter Python 3 command. So here on my computer I have Python installed and I am able to run such application directly in the terminal without Docker. If you are a PC user, you might probably not have Python installed on your computer, right? And also, even if it is installed, you might want to run your Python application using specific version of the Python. And that specific version may not be that version which you have installed on your computer. So, let me first try to run this application using Python interpreter directly on my computer. If you don't have Python, no worries, just watch what I'll do right now. So, I could enter Python, and afterwards name of the file which contains actual Python application. In my case, inside of the python-app folder, there is main.py file. It seems to me I didn't move it to python-app folder, now it is inside of that folder. So, yeah. And now let me use Python command, actually Python 3 command, in order to run main.py file. Let's run that. And I see prompt, please enter any positive number which comes from this line of code. Let me enter number 5, for example. And here I see result, sum of all positive numbers till 5 is 15. 1 plus 2 plus 3 plus 4 plus 5. Alright, application works, and notice that when I saw this result in the terminal, application actually was terminated, was exited, because there is no need to run application further, because it performed already all its tasks. So, when Python interpreter reached the end of this file, it actually exited this application. Alright, that's how I am able to run this Python application directly on my computer without Docker. But what if you want to run this application using Docker container? If, for example, you don't have Python, or if you want to run application using specific version of Python. Let me show you how to do that. We could very easily pull Python image from the Docker Hub, create corresponding container based on that image, and run this application inside of that container very easily. And now we have to answer question how we will actually copy this main.py file to the container where we want to run this file. Answer is very simple, using volumes mapping, which we discussed before. So let's use docker run command in order to create container using a Python Alpine image, this smallest Python image available, and we will use volumes mapping in order to map this file to specific volume inside of the container, and afterwards execute that file inside of the container. So now I'm in the python-app folder, and let me docker run. Here let me run it with options -it. Next let's add volumes mapping -v, and I'll map current folder, it is python-app. Let me use syntax which we used before with variable. Here will be pwd, and I'll simply take all contents of python-app folder and move them to /app folder inside of the container, like that. And afterwards I'll specify which image I want to use in order to start this container, and it will be python::alpine, smallest Python image available. Alpine here is tag. And afterwards I'll specify which command I will run when container will be started. And I want to execute main.py file, which will be located in the /app folder inside of the container. And for that I could utilize command, after space I type Python, and again one more space, and type here path to executable Python file. And it is located in the /app/main.py file. Very easy. So I'll create container based on this image, python::alpine. Here I create volumes mapping and map python-app folder with all files inside. Basically we have only one file there, main.py, to the /app folder inside of the container. And when container will be started, this command will be executed, and Python interpreter will launch main.py file located in the /app folder. Simple as that. Notice that here I don't have to specify specific version of the Python using Python 3 or simply Python command, because there is only single version of the Python available inside of such image. Alright, so let's run that and let's create container. Unable to find image Python Alpine locally, pulling from library Python. And notice that some image layers already present in my Docker cache, because before I actually already pulled Python image. And here I see prompt from my application. Please enter any positive number. Let's enter, for example, number 10. Sum of all positive numbers till 10 is 55. So application did work, and it was launched inside of the container using Python interpreter available inside of the created container. Right? It is very, very important. Python interpreter on my computer was not used for that. And second important note, after this output, Python actually exited this application. So there was no need to run it further. And basically after that, there were no other processes running inside of that container. And in such case, Docker automatically stops such containers. They are no longer running anymore. That's why if I enter now command docker ps, I will see empty output because Python container was automatically stopped by Docker. Application did its job. Container was single purpose to run this application, and therefore Docker decided to stop it. If I enter docker ps-a command, I'll see that there is stopped container with such ID, such name, image is python:alpine, and it was exited several minutes ago. Here is actual command that was utilized in order to start actual container and run specific application. Alright, that's how I was able to run this Python application inside of the Docker container. It was relatively easy, and in such way you could basically run any application if you will find corresponding capable Docker image for that. Alright, but now question. What if your Python application has some dependencies which have to be installed before actual launch of the application using Docker container? In such case, you will not be able to utilize such official Docker image which we just used, because it does not have all necessary dependencies which you probably need for your application. In such case, you will need to build your custom image based on one of the official images. And that's what we will discuss next. We just successfully executed specific Python application inside of the container, and it was relatively easy. Why? Because our application didn't have any external dependencies, and therefore we were able to utilize just official Python Docker image in order to run our application inside of the container. But what if your application has some specific requirements and depends on other packages? It shouldn't be necessarily Python application. I'm talking about any application which you could run inside of the container. In such case, it's not enough to use just official Docker image. You have to build your own custom image. And in order to do that, you have to utilize Docker files and Docker build command in order to build such custom image. And in this lecture, let's talk about that in details. So, Dockerfile is just a text file with set of instructions for creation of the custom Docker image. And the process of the creation of the custom image and container is following. You create a Docker file. It is just text file with some instructions. In each Docker file, you must specify base image which you would like to utilize for your custom image. Recap that each image actually consists of multiple file system layers, and you'll basically build your custom image on top of those base FS layers and add additional FS layers. So, first step is creation of the Docker file. When Docker file is created, you could utilize Docker build command in order to start build process and build custom Docker image. And you could also name this custom Docker image. And usually such name includes actual name of the image and tag. But if you are planning to push this customly built image to Docker Hub, you should create account at Docker Hub, create username, and prepend your username to the name of the image if you want again to push your customly built image to Docker Hub and reuse it somewhere else. And basically, when image is ready, it has name, it has tag. Of course, it is also possible to create different tags for the same custom image. And afterwards, you are very easily able to create a new container based on that image, using, for example, docker run command or docker compose. This image, which you just built, will be located in your local Docker cache. It will be available for use locally, but if you push it to Docker Hub, it will be available for use also at Docker Hub, and you will be able to pull it from Docker Hub. Alright, that's process. So first create Docker file, then build image based on that Docker file, and finally launch one or several containers based on customly built image. Let's have a look at the docker build command. Here it is. It builds new Docker image from specific Docker file. This file has actually this name, Dockerfile. And this command, docker build, consists of following parts. Docker, which is a reference to Docker client, then build. It will actually tell Docker that you want to build new image. Then comes a reference to the folder where Docker file is located. And if you already changed directory in the terminal to the folder which contains actual Docker file, you could simply specify here a dot. Dot is relative path to current directory. If Docker file is located in another folder, you could simply specify here a path to that folder, either relative or absolute, doesn't matter. So it is location of the Docker file. Afterwards, you should add a tag using -t option. And here is sample tag, my image :tag. My image will be actually name of the newly built custom Docker image. And after colon, you could add tag, for example, first, second, and so on, or latest. But if you omit tag section, then latest tag will be added by default. Also, if you are planning to push customly built image to Docker Hub, you have to prepend here your Docker Hub username. For example, bstashchuk / then my image :tag. So username / name of the image and afterwards optional tag. This build process will go through the Docker file and perform all instructions which you write there. And basically, this process will create new FS layers on top of the FS layers which are already present in the base image in Dockerfile. And at the end of this process, you'll get actually custom Docker image and you will be able to create new containers based on that image. Alright, here is very simple Docker file with 3 instructions. Instructions are actually in uppercase and they are, for instance, from, run, or cmd. In this Docker file, using from instructions, we specify base image for our custom image, and it is Ubuntu. Tag here is omitted, therefore image with latest tag will be pulled from Docker Hub. So this is base image which will be utilized for our custom image. Next, here is instruction run, and using this instruction we could perform some actions. For example, here you see apt get update command, which will essentially update a list of packages inside of this newly built image. It will not install any dependencies, it will just update the registry of all packages. And finally, here is command cmd echo welcome, and it is that command which will be executed when new container will be created based on this newly created image. And essentially all what it does is prints welcome to the terminal using echo command. So very simple Docker file just with 3 instructions: from, run, and cmd. From instruction must be present in any Docker file. It specifies custom image. Alright, let's have a look at this very simple application which we will build in this course. It will be a Python application which will interact with Mongo database. And this Python application will require actually external Python dependency called, for example, PyMongo. It is a module which will allow us to interact with Mongo. This PyMongo package is absent in the Python by default, therefore we have to install it using Python installer. And it means that it's not enough to utilize just official Python image. We have to build our own custom Python image for that. And we will create, of course, for that Dockerfile. Next, we have to run one more container, and it is Mongo container. And in some way connect those two containers together. So Python container should be able to access Mongo container running on the same Docker host. First, we will run those two containers using docker run command, of course, after we build a custom Python image. And you'll see how to connect those two containers using docker run command. And afterwards, we will move on to Docker Compose and create both containers using just single command docker compose up. Alright, let's get started with that, and the first step is the creation of the actual Docker file. And of course, I'll demonstrate you now how actual Python application will look like. It will be very basic, but main idea here is that this Python application needs to interact with Mongo. So let's get started with that after the pause. We just discussed what is custom image and how to build it using a docker build command, and for that you require Dockerfile, which is located in one of the folders on your local computer. And now it's time to build this very simple application, which will contain two containers, Python and Mongo. And we will first create such Python application that will actually consist of just single main.py file. Next, we will create a Dockerfile in order to build custom image. And finally, we will launch two containers. Python container, which will be based on newly built custom Docker image. And the second will be Mongo, and for that we will utilize just official Mongo image. Let's get started with that. Let me close this main.py file, I don't need it anymore. Let me hide terminal for the moment, and let me create a new folder here. And this new folder will be, let's say, Python custom. Inside of Python custom folder, let's create a new file, main.py. And in this file, I'll paste contents of actual Python application. Here they are. This Python application is very basic. But in this application you see that we utilize external module called pymongo. And from that external module we import Mongo client. And here you see Mongo URL, which is equal to MongoDB ://Mongo. Mongo is actual host name of the server where we will run Mongo. And going two steps ahead, this will be actually equal to name of the Mongo container. And here is default MongoDB port. So here is Mongo URL. And afterwards we create client using Mongo client. And here we pass Mongo URL as argument. So we basically create a new instance of the Mongo client class. Next, we select specific database and execute very simple command, list databases. And this command will actually return us list of all MongoDB databases. By default, if there are no records in the database, in the MongoDB, there will be 3 default databases, and we should see all of them here when we will print to the terminal db's list variable. By the way, pprint will pretty print this object, and pretty print module is available in Python out of the box, therefore we don't need to install it separately, but pymongo is absent. And that's why here now in Visual Studio Code you see that pprint is not underlined, and VS Code correctly recognizes that pprint is available because I have Python installed on my computer, but pymongo is underlined. Import pymongo could not be resolved. It means that VS Code IntelliSense is not able to locate this module, because this module is simply not installed on my computer. Therefore, in order to run this very simple Python application, we have to create corresponding custom Python image and install their PyMongo package before we will run our main.py file inside of that container. So let's save main.py file here. And basically, if you want, I could demonstrate to you that locally I will not be able to run this application. Let me try that. So let me go out of Python-app folder to Python custom. And here let's enter Python 3 main.py. I am in the Python custom folder where this main.py file is located. Here it is. So let's run this file. And here I see error. Module not found error, no module named PyMongo. And that's what I just told you. This module is not installed on my computer, therefore I am not able to run this application. Alright, let's now create a Dockerfile. Let's go to Python-custom folder, and here inside we will create one more file. And its name will be starting with uppercase D, Dockerfile, simple as that. And VS Code will immediately recognize that it is a Docker file. Here you see Docker icon. Alright, Dockerfile without dot, without anything, simply Dockerfile. And here inside of this Docker file, let's add instructions how we will actually build our custom Python Docker image. And first instruction here will be from, and using from we specify base image for our custom image. And base image here, let me hide terminal, and base image will be Python :Alpine. It will be enough to use just the smallest Python image available. And by the way, here you see suggested list of all possible tags. In order to see such outputs, you have to install Docker extension in Visual Studio Code. In order to do that, please go to extensions here and search for Docker. I already have such Docker extension installed. If you don't see it here installed, please go ahead and install it. So, here I see first instruction. Let's go ahead, and next instruction will be work dir. Notice that as I type, VS Code suggests me specific actually steps, because each instruction here is separate step in the building process. So work dir. And here will be path to working directory inside of the image. Why is that? Because except your application files inside of the image, inside of the container, there will be other folders like bin, sbin, and so on. And you should not place your application-specific files like main.py file directly in the root of the file system of the container. Therefore, let's specify here a path in following way: /up. Simple as that. You could also specify longer path, for example, my/up. And in such case, Docker will actually create all missing folders inside of the image. So first it will create my folder, and inside of it, it will create up folder. But in our case, it will be enough to have just a single up folder where we will place our application-specific files. And our application at the moment has just a single file main.py. Alright, that's work dir instruction. Next instruction will be run, and using such instruction we could run specific command while building new custom Docker image. And we would like to install dependency called PyMongo. And dependencies in Python could be installed using pip. Pip is Python installer. Simply type pip install PyMongo. And on this step, Docker will actually run this command and install PyMongo inside of the image. And of course, pip will be available here at this step, because we utilize base Python image, which comes with pip installer out of the box. That's why we will be able to install PyMongo using pip install command. Alright. So after this step, PyMongo will be available inside of the image, and we will be able to utilize it in our application. So, next step. On the next step, we have to copy our application files from this folder, Python custom, to the app folder inside of the container, to this working directory. And for that, we could utilize copy instruction. Copy from source to destination. Dockerfile is located in Python custom folder. Therefore, here we could specify a relative path to our application files using simply dot as source. So dot will represent Python custom folder where Dockerfile is located. And next we should specify destination. And here you see suggestion /app. That is actually absolute path inside of the container, inside of the image actually, because we are now building new image. So you could type /app like that. It will point to this working directory inside of the image. Or you could use relative path, dot. And relative path here at this moment will be actually up, because when you add instruction workdir, Docker will actually change directory to this working directory /app. And at this moment, dot will actually point to this /app folder. But in order to avoid any confusion, we could specify here /app. It is absolute path to app directory inside of the image. So we copy all files from our local directory where Dockerfile is located. Here is this directory, to /app folder inside of the image. And why we should do that? Because we want to make our customly built image fully independent from our local file system. And therefore, such image could be utilized on any other computer in order to run our Python application, because it will have main.py file, which is actually just a single file in our application, available inside of the image. So no need to create volumes mapping in order to map all files from our local computer to container when we start such container. So this application file will be available inside of the container after we create such container using a customly built image, using such instructions. So here is copy instruction, and at the end there will be cmd instruction that stands for command. And here you should add executable, which you want to run when corresponding container starts based on this customly built image. And we want to run main.py file, right? Using Python. So executable here will be Python. And as second element in this array, we should specify parameters for this executable. And name of the file which we want to run is actually parameter for Python executable. Therefore, here in double quotes, write main.py. You don't need to specify a full path to main.py like that. You could actually do that, but you could simply specify a relative path to main.py. Because, as I told you before, Docker will actually cd, change directory, to this working directory, and at this moment, when you run Python main.py file, it will know that main.py file is located, should be located in the /app folder, and it will look for this file here inside of the app folder. Alright, that's all what we need in order to create a Dockerfile for our custom Docker image. Let's now save changes in this file, and next, after the small pause, let's try to build Docker image based on this Dockerfile. And afterwards, we will also run container based on this customly built image. I'll see you guys next. We just successfully created a Dockerfile and a very basic Python application, which will actually list just databases on Mongo and print result to the terminal. But in order to perform such task, we needed to install pymongo, which is actually external package for Python. And also, second, we have to run Mongo container in order to be able to perform such action inside of the Python application. So we have created such Docker file, where base image is Python:\alpine. Working directory specifies where Docker build process will actually put all application files, which we will copy here on this step. Next, we install actually PyMongo using pip install PyMongo, and finally we run main.py file using Python executable file. And these CMD instructions will be actually performed only when container starts, container which is based on this customly built image. And at the moment this image is absent, and we have to build it first. And here is our Python application which will connect to Mongo and execute this command list databases, and afterwards, if connection was successful and MongoDB is running here at this URL, then this Python application will print a list of the databases here to the terminal. Alright, let's now build our custom Docker image. Let's go to the terminal, ensure that you are in the Python-custom folder, this folder where we have created Dockerfile. It is very important. And here inside of this Python custom folder, let's enter docker build command. Docker build. Next, here we specify path to the folder where Dockerfile is located. We could specify just dot, it is relative path to current directory, to this directory. Next, let's add tag to our new image using -t option, and the tag will be, let's say, Python custom, same as name of our folder. We could specify here also tag, for example, tag first. But if you omit tag here after colon, then tag latest will be added automatically. Also, if you are planning to push custom image to Docker Hub, then you should prepend here your Docker Hub username. For example, in my case, it will be like that. My username / and then name of the image. But I am not planning to push this image to Docker Hub, therefore I could simply name it like that, Python custom, and it will be present only in local Docker cache. Alright, we are good to go and we are ready to start build process. Let's start it. First, let's observe this process, and afterwards I'll explain to you step by step what actually happened. Let's wait a bit. So, image was built, and now let me scroll up to the very beginning of this output. So first, at this first step, here you see instruction from, and that is that instruction that is placed in the Dockerfile on the very first line. On this line, we specify that we want to utilize Python:\alpine image, and that's where it is pulled from the Docker Hub. But basically, we already had this image locally in the local cache, because before we already pulled this image from Docker Hub when we run Python application. Therefore, Docker just utilized this image from cache. On the next step, we specified a working directory /up. Step number 3, run pip install pymongo, and you saw that Docker has actually installed pymongo dependency inside of the image. And here you see that this step took around 10 seconds. And finally, we copied all our application files from the local folder on my computer to /up folder inside of the container. And that was actually last build step. And what Docker essentially does on each of those steps, it creates brand new file system layer. So here is new FS layer, here is new FS layer, and here is also new FS layer. It means that on top of this base image, this build process has created 3 additional FS layers in the custom Docker image. And at the end, it exported layers and created new image with such hash. And it named this Docker image, as we specified in the command, Python-custom. And now such image should be present in our local cache. Let's verify that Docker images. And yes, here is Python custom image. Its tag is latest, and this tag was added automatically by Docker. because we didn't specify any custom tag. Here is image ID, and here is size of our custom image, 57 megabytes. Notice that our Python custom image is based on this base Python image, Python Alpine, and the size of this base image is 45 megabytes. It means that we added around 12 megabytes on top of this base image, and that's actually size of PyMongo client, plus size of our application files. Alright, that's how we build our Python custom image, and now let's actually try to run a new container based on this customly built Docker image. And inside of that container, we expect to run our Python application using python main.py command, which is already hard-coded in the custom image which we just built. And now this custom image actually contains this file. Alright, let's go ahead and try to create a Python container based on this Python custom image. For that, let's enter docker run. Next, let's add also -it options. Next, specify name of the image. It is python-custom. We could omit tag because tag is latest. And here first, let's simply run it like this. Docker run -it python-custom and see what will happen. Running. And now I see error actually. It was a long time after entering this command, and finally I see traceback. File up main.py, line 7. Here in database.py there is actual error. And error actually tells us that Python application was not able to connect to MongoDB. And here, let me basically quickly hide the camera here. And here is error, name does not resolve. Because we specified the URL string for connection to Mongo as Mongo:port, and Python application was not able to resolve this Mongo name to IP address. That's why it thrown an error, name does not resolve, and the Python application actually crashed. That's what just happened. But basically you see that at least we tried to start application itself. It was an attempt. And now let me show you one more thing. Let's try to create one more container based on the same image. By the way, container which we just started is now stopped. Let me quickly verify that docker ps-a. Here is this Python custom image, and here is container which was exited 1 minute ago. And here is command which was utilized to run this container, python main.py, and this command matches with this command here in the Dockerfile. Alright, so now this container was exited and is now stopped, and now let's create one more container based on the same Python custom image. And now, instead of actually launching Python application, let's override command which will be used in order to start container. And let's simply start SHA shell inside of the container. SHA shell should be available here. So let's go ahead. And now I am inside of the container. Notice that I was automatically placed inside of the working directory, which was specified here by work_dir instruction. And if I list files and folders here, ls, I see Dockerfile and main.py files. That are actually contents of the python-custom folder, which we copied to the image at this step, copy./up. We copied all files from the folder where Dockerfile is located. Alright, so here I see two files in the up folder. But what if I go one level up out of the up folder and list files and folders here? Here I see basically file system of this container. And it contains such folders as dev, etc, lib, mnt, and so on. All those folders are actually system folders. And recap that before I told you that you should not place your application files directly in the root of the file system in the container. And that's what I meant. you should create separate folder, for example, app, and place your application-specific files there, and not pollute this root folder where all subfolders like root SRV are located. So please always create separate working directory and place your application files there, like is done here for this particular image. Alright, so that's how our custom container looks from inside, and let's exit from this shell inside of the container. And now, after the small pause, let's run Mongo container along with a custom container based on our customly built image, this one. And afterwards try to launch Python application again and see whether we will be able to connect actually to Mongo container or not. I'll see you guys next. We just successfully created new container based on the customly built Docker image, and we built it using a custom Dockerfile with several instructions. And now it's time to launch Mongo container and try to launch Python application again and see whether it will be able to connect to Mongo container and print list of databases there or not. Let's try to do that. So, we already have Python custom image here on the list, and now we should create Mongo container. And let's create it in following way. First, let's verify which containers are running here, Docker PS. There are no containers running. And let's create Mongo container using docker run command, docker run. Let's run it in detached mode, -d. Next will be -- name option, and with such option you could specify custom name for the container. Recap that by default Docker generates such names randomly. But we have to specify specific name, because we want to connect to that Mongo container from Python container using such URL. We want to resolve Mongo hostname to IP address of the Mongo container. So let's specify name using -- name option, and name for Mongo container will be Mongo. And afterwards let's specify actual image we want to utilize for this Mongo container, and it will be simply Mongo. And latest tag will be applied by default. By the way, here between -- name and the actual name of the container, you could add equal sign like that. So let's run this command and create a new Mongo container. Unable to find image Mongo latest locally. Now it will pull image from the Docker Hub. Let's wait a bit, because image is relatively large. So here I see that specific FS layer, this one with such SHA-hash, is around 200 megabytes. So it is relatively large. So this image is almost downloaded. Now it is extracting. Notice that this particular image consists of multiple FS layers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 FS layers. Finally, image was downloaded, and if I list images now, Docker images, I should see Mongo image with latest tag with such ID on this list, and the size of this image is 700 megabytes. And it is basically size of extracted layers, because by default we download actually zipped FS layers from the Docker Hub, and afterwards we extract them here locally on our computers. So Mongo image is available, and now if I enter Docker PS, I should see that Mongo container with name Mongo, it is custom name, is up and running. And here is default MongoDB port, which is open inside of this Mongo container. And it means that we are now actually able to connect to this container. Let's have a look at logs of this container, Docker logs. And here we could simply type name of this container, Mongo, Docker logs Mongo. And here are logs which come from this container. All right. Now let's also enter docker inspect command and inspect this. Let me actually enter again name of the container, Mongo, like that. And here I'll find, for example, IP address assigned to this Mongo container, 172.17.02. Also, if I scroll a bit up, I'll find in the ports section ports which are open inside of this Mongo container. And there is just single open port, this one, and it is TCP. Great. Let's now run our Python container again, based on our custom image, Docker images, this one, and see whether now we will see some meaningful output from our Python application. So let's docker run -it. Here will be Python-custom, name of our custom image, and let's simply run it like we did before. Recap.mongo container is now up and running. Let's go ahead. Again, waiting. No output from the application. And probably we will again get an error from the application. So still waiting. And finally I got this error. Name does not resolve. Timeout 30 seconds. It is default timeout. And it means that our Python application was not able again to resolve this name to IP address. But why is that? We actually are now running Mongo container with such name Mongo, and probably Docker should resolve this Mongo name to IP address of this container. But let's try to log in to container with Python application. Let's add here SHA shell. And let's try to ping Mongo. Bad address Mongo. It means that our Python container is now not able to connect to Mongo container by its name. But what if I ping IP address of our Mongo container? Ping 172. Let me actually quickly check again this IP address. Let me open up a new terminal, and here let's docker inspect Mongo. Here is this IP address. So let's try to ping this IP address inside of the Python container. Ping, and here is IP address of the Mongo container. Let's ping it, and I see response. It means that there is connection inside of the Docker between those two containers, between Python container and Mongo container. So Python and Mongo containers. And the reason for that is that by default they are attached to default bridge network, and they basically have IP addresses from the same network. And if I enter here host name, I'll get actually host name of this Python application, but if I enter here -i option, I should get IP address of the Python container, and here is this IP address. And this IP address and IP address of the Mongo container are in the same network. That's why those two containers are able to communicate with each other using their IP addresses, but not names of the containers. We just verified it. But question, how we could actually allow communication between different containers in Docker by their names in order to be able to utilize such syntax here in this Mongo URL? Because we don't want to change this URL to URL with IP address, because IP address for containers is dynamic actually, and each time when a new container is created, Docker assigns such IP addresses dynamically. Therefore, we should not rely on IP addresses. We should rely on the names of the containers instead. Therefore, we have to find a solution how to connect actually those two containers by their names. And the solution in Docker world is relatively easy, and it includes creation of the custom bridge network. And by default, if I enter here command docker network list, I'll see such networks as bridge, host, and null. And this bridge network is basically that network which is used in order to attach newly created containers. And after the small pause, we will create new custom network and attach to it two containers, Mongo and Python. And afterwards, we will verify whether a connection from the Python to Mongo will be successful or not. Let me delete this terminal, and I'll see you guys after the small pause. We just successfully started Mongo database container, and we tried to launch our Python application again, but again we got an error. And the reason for that is that now Python application is not able to resolve hostname Mongo to IP address of the Mongo container. And in this lecture, I'll demonstrate to you how to connect different containers by their names using custom Docker network. And now let's create such custom network using command docker network create. And let's create a new network named, for example, Python Mongo, because we will place there our Python and Mongo containers. Let's create such network. Network was created, and here is ID of this network. And if I list all networks now using Docker network list, I should see newly created network on the list. Here it is, Python Mongo, and it is bridge type of the network. And here is ID of this network. And now I am able to attach containers to this custom network. And containers in the custom network will be able to communicate with each other using their names. That's how Docker works. So let's now do following. First, we have to attach running Mongo container to this newly created network. Of course, we could stop and remove running Mongo container and afterwards create new with attachment to this custom network, but also there is the way to attach running container to another network. If I list containers now, I'll see that Mongo container is running. Therefore, let me attach it simply to custom Python Mongo network, which we just created here, Python Mongo. For that, you should utilize command docker network connect. Next comes name of the network, Python-Mongo, and then comes name of the container which you want to attach to this specific network. And name of our container is Mongo. So let's type name Mongo here and attach Mongo to Python Mongo network. Let's now inspect Mongo container, docker inspect Mongo, and find where is actual assignment to network. But I already see that IP address here is from different network. Before it was from network 172.17.0.0/16, but now it is from network 172.18.0.0/16. 16 is network mask. And that is an indication that this container was moved from one network to another. And here is basically network ID of the network where this container is now attached. Let me try to find name of this network where this container is attached. Actually, let me do following. Docker inspect Mongo, and here I'll use pipe and add grep Python-Mongo. And yes, here I see actual name of the network where this container is attached. Let me actually try to find it here in this output, Python Mongo, like that. And yes, here I see this section, Python Mongo, and basically here is network ID, and here is IP address of this container, Mongo container. And here is default gateway inside of this custom network. Alright, Mongo container is attached now to custom network, Docker network list, this network which we just created. And now let's run our Python container also attached to this custom Python Mongo network. For that, let's utilize command docker run same as before. Let's run it in interactive mode, IT, and here let's add option -- network. And here after equal sign, let's specify name of the network we want to attach this container to, Python-Mongo. And finally will be name of our image we want to use for creation of this container. It is Python-custom, like that. Let's now run our container. And now I see output in the terminal. And the output actually contains list of databases from the MongoDB. and there are such databases as admin, config, and local. And it means that now our Python application actually worked as expected. Let's try to create one more container using same command, but now let's run SHA shell here and go inside of the container. We also attached it to custom Python Mongo network, and let's now ping Mongo container using just name of the container, ping Mongo, and now I get a response. That's how it works. In the custom network, containers are able to communicate with each other using container names or even container IDs. But using container IDs is not really convenient because they are randomly generated. That's why it makes much more sense to communicate between containers using their names. And of course, in such case, you have to specify custom names when you create new containers. Alright, now our application works and the Python and Mongo containers are now able to communicate with each other. And basically, let me launch container once again, Python custom, without SHA executable here at the end. And I again see result here in the terminal, list of databases. And of course, when our Python container does its job, it actually exits and container is stopped. If I enter Docker PS, I should see only Mongo container which is up and running. There is no Python container because it was stopped. If I enter Docker PS-A, I could verify that. Here is a bunch of different Python custom containers, and notice that IDs of those Python containers are different. Each time when a new container is created, new ID is assigned to it by Docker. And basically here you see that I started this container with custom command, SHA shell. And here we started container with default command, which is hard-coded actually by build process, and this command was specified in the Dockerfile. Alright, let's now also quickly check logs of the Mongo container, docker logs Mongo, and here I should see that there was connection, and here I see connection ended. Let me scroll a bit up. Interrupted operation as its client disconnected, PyMongo. So here I see that there was connection from PyMongo. Here is a version of the driver. And somewhere here I should find also IP address. Yes, here is IP address of the remote server which connected to this Mongo server. So here is IP address of Python container. Alright, that's our logs of Mongo, and that's basically it for this lecture. And now you know how to build a custom image using Dockerfile. So here is Dockerfile which we created for our Python application. Here is actual Python application. And we started two different containers. Actually, we attached them to custom network, which we created in order to be able to communicate between containers using names of the containers. And the connection now is successful from the Python to Mongo. But we actually entered two different Docker run commands in order to run two different containers. So first we started Mongo container, and afterwards we started Python container. But imagine that your application consists of 10 different microservices, which includes, for example, multiple database services. And of course, running all those containers manually using docker run command and attaching them to custom network is not really convenient. That's why there is a tool in Docker which is called Docker Compose, which allows you to combine everything just in one step and start multiple containers simultaneously. And Docker will create for you custom network. It will automatically launch necessary amount of containers, and when you enter Docker Compose down command, everything is destroyed by Docker. It is very, very convenient, especially for development purposes. That's why let's, after the small pause, move to Docker Compose and migrate our tiny application Mongo plus Python to Docker Compose. I'll see you guys next. We already covered a lot, and we just connected two different containers, Python and Mongo together, and we were able to perform some operations in the Mongo container from the Python container. And for that we actually started two different containers using docker run command. But usually it's not convenient to run multiple containers using docker run command, especially if you want to start multiple containers. And that's why there is a very nice Docker feature which is utilized very often during development of different applications locally, and this feature is called Docker Compose. And it is actually last feature in this Docker crash course, and let's have a look at this very simple Docker Compose configuration file. Because in order to run several containers, you have to create instructions for Docker how it should actually run those containers. And those instructions are placed in the Docker Compose configuration file. Here is an example of such file. At the top you specify version of the Docker Compose, and last version is 3. And below you specify a list of services which you would like to start. In this example, there are just two services, app here and Mongo here. It will mean that Docker will essentially start two different containers with corresponding names, app and Mongo. Also, Docker will automatically create a corresponding custom network, and it will place all newly created containers inside of that custom network. Also, here in this configuration file, you could specify how you would like to start specific container. For example, here you see that for app service there is build instruction. And before starting actual app service, it will build custom image using instructions inside of the Docker file, which is located here in this folder ./app. So first, custom image will be built, and afterwards new container will be started based on that image. If image was already built before, then Docker Compose will simply reuse already built image. Here for second service, Mongo service, you see that there is no build command. It is actually command for Docker Compose, and there is image command instead. And it means that for such specific service, which is called Mongo, we would like to simply utilize official Docker image from the Docker Hub, and the name of this image is simply Mongo. And all what Docker will do on this step, it will simply download corresponding image from Docker Hub if it is absent in the local cache. And here next in this example you see ports instruction. And using such instruction, you could open actually ports inside of the containers. And using such instruction, as you see here, we actually allow connection to port 27017 on our local computer. And this connection will be proxied to container. Basically, using Docker Compose, you could perform all kinds of operation which we discussed before. You could configure volumes mapping, ports mapping, as you see here, set environment variables, and many more. Also, as you see in this example, it is even possible to build custom images, like you see here in this example. But what is the structure of this Docker Compose file? How you should place those colons here, tabs or spaces, what is that? It is actually YAML language. And YAML language actually is used in most cases for setting different configuration parameters for applications. In this markup language, you could specify either lists or dictionaries, very simple. Dictionary is actually a set of key-value pairs, where key comes before colon, and after colon you specify actual value for specific key. In the list, you specify list of elements. For example, here key is fruit, and in the list there are banana, orange and apple. Here you see dash in front of each item. In the dictionary, you could also utilize nested dictionaries like you see here in this example. Here pen is key and its value is here. This value itself is dictionary, which consists of multiple key-value pairs, color yellow, model, and value of the model is actually nested dictionary. These indentations here are very important. That's how YAML is structured. And indentations consist of spaces. You could use either 2 spaces or 4 spaces. Please be consistent. In one file, don't mix 2 and 4 spaces. Don't utilize tabs. And basically, most modern editors replace tabs, if you press them on the keyboard, with spaces, either 2 or 4, depending on the configuration of your editor. That's YAML, and that's that format which is utilized in order to create a Docker Compose configuration file. And next, after the small pause, let's move our tiny application, Python plus Mongo, to Docker Compose and create very simple YAML configuration file, and afterwards run 2 containers simultaneously. See you next. Alright, let's now go ahead and create Docker Compose file for our Python plus Mongo application. And for that, let's create a separate folder here. Basically, I don't need this Docker file and this main.py file here. Let's create a new folder here and let's name it, for instance, Python-compose, like that. Here inside, let's create new file and let's name it Docker-compose. And extension will be YAML. Please type name of this file exactly as I just did. And notice that VS Code recognized type of this file, Docker Compose YAML. Alright, this file is now available here inside of the Python-compose folder. Now let's create a folder for our actual application inside of the Python-compose folder. And the name of this application will be simply app, like that. And let's put 2 files from the Python custom, namely Dockerfile and main.py file, in this app folder. You could copy them, Command-C on Mac or Ctrl-C on Windows, then select app folder and paste them like that. So now Dockerfile and main.py file are located inside of the app folder here, in the Python-compose folder. And if you have multiple applications which you would like to start using Docker Compose, it's a good convention to create separate folders for each your application. And in the root of your project folder, create Docker Compose YAML file, which will describe all services which you would like to start using Docker Compose. For example, if you have, let's say, front-end application, please create a front-end folder. If there is also back-end service, create one more folder, like that. And afterwards, inside of the Docker Compose file, specify instructions how to start all those applications. Of course, if you want to utilize some official images from the Docker Hub in your Docker Compose file, then there is no need to create separate folders for those services. For example, now we will start a Mongo service along with Python service, and we don't need to create a separate folder for Mongo service here. So we just create our app folder for our Python application. Alright, so we created app folder in the Python Compose folder, and there is Docker Compose YAML file. And now let's fill in this file here. Let me hide backpane and terminal, and instructions here will be as simple as you see here in this example. But first we will not specify ports here. So let's add here version. Version here will be 3rd, it is last version. Next will be services. Here, by the way, you are able to auto-complete everything because I have Docker extension installed inside of the VS Code. I also recommended you before to install it. If you don't have it, please go ahead and install it. Here is this extension. So, services, and here I could actually use tab, but basically I could see that tab is replaced by 2 spaces. And I use 2 spaces because of this configuration here, so 2 spaces for 1 tab. After tab, please write name for first service, and it will be, let's say, app, our application. After colon and tab, let's specify how we actually want to build our application, and here we will specify build instruction. Build. And as a value will be path to the folder with corresponding Docker file. And Dockerfile for our Python application is located inside of the app folder here. And we could specify relative path to app folder, and inside of it there is Dockerfile here. So path here will be ./app like that. App is name of this folder again. And that's all what we need in order to actually create app service. So just specify path to corresponding Docker file. Next, let's add also one more service. Please ensure to place this service underneath this service. So second service will be Mongo. And we here specify simply image. And we would like to utilize image called Mongo. And it will be downloaded from Docker Hub if it is absent in the local cache. So image is Mongo. And that's basically all what we need in order to bootstrap our Python plus Mongo application. Using such configuration, we will create two different services, app and Mongo. Here for this service, we will build a custom image if it is absent, using instructions located in the app folder. And instructions are, of course, read from the Dockerfile. And for this service, we utilize default Mongo image available at Docker Hub. Simple as that. Let's save changes in this YAML file, and let's open up terminal. Let's check which containers are now running here, Docker PS, and I still have Mongo container running. Now it's a good time to stop this container. We don't need it anymore. So let's docker stop Mongo. And now let's basically remove all stopped containers. Recap that for that we could utilize such shortcut, docker rm. Here will be $, and in parentheses will be docker ps-a-q, which will actually give us list of IDs of all containers, either stopped or running. But now there are no running containers, all of them are stopped. That's why it is safe to immediately remove all stopped containers. Let's go ahead. Containers were removed, and now I don't have any containers either running or stopped. And also let's list networks, because before we created custom network. So docker network list. And yes, here is still this custom network, and now it's a good time to remove it as well. Docker network remove Python Mongo. Let's remove it. Network was removed, and now there is default list of networks. Alright, we are ready to move on with Docker Compose. Make sure to cd to necessary folder which actually holds Docker Compose file. Let me go out from the Python custom folder and go into the Python Compose folder which we just created and where we actually placed this Docker Compose YAML file. So here is this folder with Docker Compose YAML file inside. Great, so we changed directory to this folder like that, and here let's enter following command: docker-compose up. Also, there is an option to write this command without this dash, because now it is available as a command of the Docker. So docker space compose up. Let's go ahead and see what will happen. Building, and I see some output. So let's scroll to the very beginning of this output and observe what actually happened. Here we see building step. And in this step, Docker essentially built image for app service, this one. And actually you see that it reused several cached layers for this step, and for this step. And the reason for that is that before we already built image using same instructions located in Dockerfile. And therefore Docker was able to reuse such cached layers. There was no need to recreate such a first layers. Finally, Docker exported layers and created corresponding image, and name of that image is here python-compose_up. So this name consists of actual name of the folder where we placed Docker Compose file. It is Python-compose. So here it is. And after underscore, there is name of corresponding service for which Docker just built custom image. And this service we called up. That's how it is written in the Docker Compose configuration file. So here is prefix, which is name of the folder, and here is name of the service. Alright, so that's step for first service. Afterwards, we see such step as running, because there was no need to build custom image for second Mongo service. And all what Docker did, it actually created custom network, and it created it automatically. So here is network Python compose default, and here is name of actual network Python-compose underscore default. Again, Python-compose is name of the folder where Docker Compose file is located. And afterwards, two containers were created. Name of the first container was Python-compose-mongo-1, and name of the second container is Python-compose-up-1. And structure is very similar to what we see actually here, but now we see folder name, then name of the service and number. It is actually possible to run several containers for each service. But with such configuration as we entered in our current Docker Compose file, we create just single container per service. That's why here we see suffixes 1. And finally, we see step attaching to Python Compose up. It means that this container and this container were attached to customly created network. This one, this network which was created on this step. Alright, so that's how it looks like. Let me zoom out. And afterwards we see actual logs which come from the containers. Here we see logs from the MongoDB container. Here, here, here. And if I scroll down, I should see logs from the app container, our application container. Here they are. Python compose up1. And actually I see output with list of databases. And that's actually what our Python application does. It sends a request to Mongo and lists databases there, and afterwards just prints them to the terminal. After that I see also logs from Mongo, connection interrupted, because client from the Python has actually disconnected after this output. And at the end, not at the end here, I see that Python application exited with code 0. Code 0 means that application exited correctly, it did its job, and finally application stopped its process. And therefore, corresponding container, this one, was automatically stopped as well. But Mongo container is still running. Let me actually open up a new terminal. And here in this new terminal window, let me observe what actually happened. First, let me enter Docker PS, and here now I see only single container running. Here is name of this container. This name is actually custom, and it was created by Docker Compose actually when it was launching all services. Here is image which was utilized in order to start this container. And if I enter Docker PS-A, I should see stopped container. And it was based on Python compose underscore up image, which was customly built on the first step. Here is name of the corresponding container, Python compose up1, and this container exited 5 minutes ago. Let's also list networks, Docker network list. And here I see such network as Python-compose underscore default. And this network was also created automatically by Docker Compose. And because it is a custom network, it was possible to communicate between containers by their names. And that's why we saw correct result from our Python application. It was able to connect to Mongo container by the name, actually host name, of the Mongo container, which we specified here on this line, Mongo. Alright, let me close this terminal and let me terminate this process here. Ctrl-C. And what I see here, I see that those two containers actually stopped. And if I enter docker ps-a now, I'll still see those containers here, but they are marked as exited. So this one exited 7 minutes ago, and this one exited almost now. And if I enter docker ps, I will not see any containers running. But if I enter docker network list, I'll still see such custom network on this list. And in order to remove everything related to our application, you have to enter following command: docker compose down. And this command will actually remove created containers, removing this container, and removing network Python compose default. And now I don't have any containers, and I don't have custom network here in this list. That's how, using just single command, you could start multiple containers, and also using another single command, docker compose down, you are able to clean everything, yeah, to remove all started containers and to remove corresponding custom network. Alright, next, after the small pause, let's modify a bit our application and let's try to write something to the MongoDB. And we will observe whether that data which we write to Mongo will be kept in place when we restart actually all services by using docker compose down and docker compose up commands. Let's try that after the pause. We already launched our application using Docker Compose, and for that we created a corresponding Docker Compose YAML file with 2 services inside. And we saw that when you enter docker compose up command, Docker automatically creates custom network, automatically builds image if needed, and also automatically creates corresponding containers and attaches them to corresponding created custom network. And when you enter docker compose down command, everything is destroyed by Docker. Running containers are removed, if they are stopped, they are removed as well, and the custom network is also deleted. Now let's expand a bit our application, and now let's try to write something to the MongoDB. And for that, let's create another folder here, and let's name it, let me close those 2 windows, and let's name this folder, for example, Python custom-links, because we will actually insert links to the MongoDB collection. And here inside, let's simply take everything from Python-compose. Let me take this folder and this file, copy them, and paste here, like that. Basically, let me quickly rename all those folders. Here will be first example, here was second example, 2 Python up, then was Python custom, then compose, like that, and finally Python custom links. So let's now modify a bit the contents of the main.py file in our last example, Python custom links. So please note that we are working now with this example. And inside of the main.py file, let's replace contents with following. And this application differs a bit from the previous application, and you could see that now, instead of printing a list of the databases which we read using Mongo client, we actually do following. We again create Mongo client, same as we did before, and connection string is here completely the same. So Mongo is the name of the Mongo container, and it is resolved to IP address of corresponding server. Next, here we actually create, if it is absent, a new database in the Mongo, and the name of this custom database is records. Next, using such syntax, we create a new collection inside of the database called links. And here on this line, we insert one new record to this collection, to links collection. And here is a dictionary which actually holds actual object which will be inserted into the database, and it has only single key value pair, link, and here is a link to my website where I list all my courses. And after this insert, we find all records in the database using find command, and for each link which will be found, because this operation will actually return cursor, we iterate here over this cursor and print to the terminal each link. Let's save changes in this file, and let's have a look at contents of our Docker file. And basically here we don't need to modify anything. So we create a custom Docker image same as before. We install py-mongo and copy all application files to app working directory. By the way, let me replace /app with dot in order to demonstrate to you that such copy operation will be also successful. And here we run our Python application same as before. Alright, Dockerfile was modified a bit, and now let's go to Docker Compose. Here let's keep everything as it is right now, without any changes, and let's run our application. Let's cd to newly created folder. Actually, I just renamed all folders, therefore let me simply delete this terminal and open up terminal again, and it will be opened in the Docker examples folder, and let me cd to our last example 5 Python custom links. So cd 5 Python custom links. And here there is Docker Compose YAML file and app folder which contains Dockerfile and all our Python application files. Let's run all containers same as we did before using Docker Compose app command. Docker Compose app. But now in order to start our containers properly, it does make sense to add also --build option, and with this option Docker will actually rebuild all images and it will not use any previously built images. So if you made changes in your application, it is always required to start Docker Compose with build option in place. Alright, let's run all containers like this and let's bring them up. Here I see in this output at the end that the application exited with code 0. And here, before this log, I see actual result of the find operation. And it means that the actual record, which I inserted to the database, was inserted correctly. And here I read it using find command. And basically here in this document, there is also _ID field. And this field is generated automatically when a new document is created inside of the MongoDB, and it has special format, object ID, and here is long number. It is hexadecimal number. But key idea here is that we were able to successfully write record to the links collection inside of the records database, and here is actual document which was inserted. And on this step, we were able to read records from the links collection. And now this links collection contains just single document. Here it is. Now let's do following. Let's stop everything and bring everything down using Docker Compose down command, and afterwards start all containers again and see whether this document will be present in MongoDB or not. Let's stop this output and enter Docker Compose down command. Please ensure that if you entered Docker space compose up command, you should enter Docker space compose down command. So please don't mix Docker -compose and Docker space compose. So please don't do that. I entered before Docker space compose up, therefore I'll enter Docker Compose down also with space here. So let's bring everything down. Container, this one was removed, this one was removed as well, and network was also removed. Let me enter Docker ps-a, and I don't see any containers either stopped or running. Now let's try to bring everything up again. Docker Compose up, creating two containers. Here I see exited with code 0, and here on this line I see again just single document. But of course ID here is different. Why I see just single document? Because we just created two brand new containers, Mongo and app. And all records which were stored in the previous Mongo container are gone. Because our Docker Compose file is as simple as that. We say that we want to have Mongo service, and we just specify image for this service, nothing else. We don't persist data. That's why each time when you enter Docker Compose down and afterwards Docker Compose up commands, brand new containers are created both for app service and Mongo service. And after the small pause, let me explain to you how we are able to persist data inside of the database using volumes. And we will actually create volume on the Docker host, not inside of our computer. So we will map volume from the Docker host to container. And this mapping will be kept for different containers, which will be started using Mongo image. So let's go ahead with that next, but before doing that, let me first open port for Mongo and connect to Mongo database using actually graphical user interface application on my computer in order to show you actual structure of the collections and single record there at the moment. And afterwards we will move on with volumes mapping. Alright, now we are able to write records to MongoDB, but we discovered that each time when we bring all services up, write something and then bring them down, all data is gone, all data in MongoDB. And when you start all services from scratch, again you get actually empty DB and you are able to write again records to this database. And first let's enable ports mapping using Docker Compose configuration file, in order to be able to connect to MongoDB from outside, from local computer. And afterwards, we will also enable volumes mapping and add persistent volume to our Mongo container. So let's start with that. And first, let me stop this output, because I'll modify actually Docker Compose settings. And first, let me enter Docker Compose down, like that. Containers were removed, and now let me go to Docker Compose file here, located in the Python custom Linux folder, this one, and here for Mongo service I'll add ports instruction. Ports, and its value is actually list of pairs of ports. And default MongoDB port is 27017, and let's actually map this port to the same port on outside. Colon 27017. And with such configuration in place, I will be able to connect to Mongo container by using local host address of my computer and such port as I see here. Let's save changes in this Docker Compose file and let's run again all services. Docker Compose app. Containers were created, and now I will try to connect to MongoDB from my local computer, and I should see this single record inside of MongoDB database. Record which was just inserted by Python application here. For connection to MongoDB, I'll utilize such application as MongoDB Compass. Here it is. And in order to connect to MongoDB, you should just specify connection string to it. And by the way, this MongoDB Compass application is free, and you could also try to install it on your computer if you want to do so. But I'll just demonstrate to you how MongoDB actually looks like at the moment. Here I don't need to specify anything, because by default it will connect to localhost and port 27017. And that's that port which I just opened from the Mongo container using a port instruction in the Docker Compose file. Therefore, I will simply press connect. Connecting, and I successfully connected to MongoDB. Here I see three default databases, admin, config, and local, and also there is records database, which we created by our Python application. And inside of it there is collection called links, And inside of this collection, there is document, as I see here, with _ID and link. And this matches with what I see here. Object ID starts with 61, so here is the same object ID. It means that now there is just a single document in the links collection, which is located in the records database. Alright, now after the small pause, let's enable volumes mapping for our Mongo container in order to be able to persist records there after recreation of the new container. Let's first bring everything down. Ctrl+C, stopped. And here let's enter Docker Compose down, like that. And we have now clean setup. And after the pause, let's add also volumes mapping. We just enabled the ports mapping for our MongoDB service, and I demonstrated to you how you are able to connect to Mongo container from your local computer using any sort of graphical user interface client for Mongo. And we verified that there was just a single document in the corresponding links collection. And when we bring down Mongo containers now, of course, all those records disappear. And now let me demonstrate to you how to enable persistent volume for our Mongo container here. And we will slightly modify this Docker Compose YAML configuration file. And let's do following. First, let's go to the end of this file, like that, to the very root, without any tabs, and here specify volumes. On the next line, after indentation, in my case it is 2 spaces, please type a name of the volume, which will be created on the Docker host. In my case, it is Linux virtual machine on my Mac. And let's name it, for example, Mongo_data. You could choose any name you like. But usually it does make sense to name volumes in such a way that you could recognize immediately which of your services will actually utilize such volume. And after the name of this volume, please ensure to add colon like that. It is required. And now we could connect this volume to our Mongo service using volumes instruction. So make sure to add volumes instruction underneath ports and image, volumes like that. It will be list of volumes. And here please type following. Use the suggestion host path container path mode or volume name container path. And we want to map a volume from the Docker host to a specific path inside of the container. And in such case, you have to simply write name of the volume. In our example, Mongo_data. Here you see suggestion, without any / or dot here in front of it. So simply name of the volume, like it is written here in this section. Next, after colon, you have to specify a path inside of the container where you want to mount this volume. And MongoDB stores everything inside of the following folder /data/db. This is absolute path to db folder inside of the container, Mongo container. And now we have mapped such volume Mongo_data, which is located inside of the Docker host, not inside of the container, to such path inside of the container. And now each container which will be started using such configuration, each Mongo container, will have access, read-write access by the way, to such volume inside of the Docker host. And if one container writes some data to such volume, and then this container is stopped and removed, and you start afterwards one new container, that new container will continue working with this volume, and data will be still persistent there. So let's save changes in this YAML file, and let's try that in action. Let's Docker Compose. By the way, let's try Docker-compose. Docker Compose up. And I will not specify build option because we don't need to rebuild actual Python image. We just modified the settings for Mongo container here and added volumes. So let's bring all containers up, Docker Compose up, creating network volume. Here I see output exited from up, and if I scroll up, I see that there is a single document at this moment of time in the database. I could verify that by going to Mongo Compass, and let's find here. I see that here is new object ID for this particular record. And let's now bring everything down, Ctrl-C, and let's bring containers down, docker-compose down. Everything destroyed. Docker ps-a. There are no containers either running or stopped. And let's now bring containers up again, docker-compose up. Containers were created. And now here I see two records. It means that data from the previous launch was persisted in the database. So here is this record, which is still present now in the MongoDB. And a new record was created by this start of the Python application. And if I go to MongoDB Compass and click Find here, I'll find two records here on the list. It means that now new Mongo container continues working with previous volume, which was used in order to write data by previous Mongo container. It is very, very important to mention that Docker Compose creates brand new containers each time when you enter Docker Compose up. And when we enter Docker Compose down again, all containers are removed, including Mongo container. Let's bring all containers up once again. Docker Compose up. Now I should see three records, and here they are. Three records which are now present in the MongoDB. And of course, if I go to Mongo Compass here, click Find, I'll see three records in the Mongo database. That's how you could very easily create volumes mapping. And basically you create persistent volume for specific service. And syntax is like that. First, using separate volumes instruction, you basically tell Docker which volumes you want to create inside of the Docker host, and name will be Mongo_data. And afterwards, you map such volume to specific service. In our case, we mapped it to our Mongo service. And syntax is here. Volumes, then here is a list of mappings. By the way, you could add multiple volumes if you want to do so, but in our case it is enough to add just single mapping like you see here. So Mongo_data is name of this volume, so here is match, and after colon we specify path inside of the container, in our example MongoDB container, and Mongo stores all data in the folder /data/db. Alright, that's it for this lecture, and let me stop this and bring all containers down. And by the way, I could enter here command docker volume list in order to see list of all volumes inside of the Docker host. And if I scroll up, I should find this newly created volume, and here is its name. 5 python-custom-links_mongo_data. So here again I see prefix for this volume, which matches with actually name of the folder where we run Docker Compose, and afterwards there is Mongo_data. That is that name which we specified here on this line, Mongo_data. And this volume is now located inside of the Docker host, and it is not inside of specific Mongo container. Alright, that's it for this lecture, and that's actually it for this course. And we already explored almost all key features of Docker, and after the small pause, let's actually summarize what we covered here in this course. That's it, guys, for this Docker crash course, and now let me quickly summarize what we've covered here. And basically we covered key features of Docker, and we compared Docker and virtual machines. I explained to you Docker architecture, and now you know Docker components like Docker client, Docker server, and you know that Docker containers are actually based on Docker images. Docker images are read-only, and they consist of multiple FS layers. FS stands for file system, and when new container is created based on specific image, new thin writable layer is created on top of read-only layers inside of the image. And you are able to create multiple containers from the same image. It is possible to reuse already present images at Docker Hub and pull them to your local computer and create containers based on them. And also it is possible to create custom images, and for that you have to create Docker files and put instructions how to build actually custom image on your own, and afterwards using Docker build command build corresponding custom image. And next to it, you are able to utilize this customly built image in order to create containers. Also, if you want, you could push customly built images to Docker Hub using your Docker Hub account. We also discussed how to launch multiple services using Docker Compose, and for that you have to create a special configuration file which has YAML extension. And inside of that file, you actually add instructions how to start multiple services. And in such configuration files, you could add port mapping instruction, volumes mapping instructions, and also add, for example, environment variables. And also, if you need to, you could also specify instructions how to build corresponding images for specific services. And afterwards, you could run all services simultaneously using Docker Compose up command. Docker Compose down command brings everything down. All containers and custom network, which is, by the way, created for each setup when you enter Docker Compose up command, are removed. That's how Docker Compose works, and that's it again, guys, for this course. And after the small pause, let me actually commit all changes and push them to GitHub in order to make all those small projects available for you. As promised, now I'll commit changes in this folder, which is called Docker Examples. And now let me create a remote repository at my GitHub account. It is bstashchuk. Here I'll create a new repository. Let's name it Docker Crash Course, like that. And here, let me keep it public, of course. I will not add README file, and let me simply create new repository. New repository was created, and here are instructions how to push changes from local to remote. First, let me add origin using this command. Let's go to VS Code. Let me open up embedded terminal here. And I'll go out of this folder. And now I'm located inside of the Docker examples folder, which has all examples like NGINX, Python, app, and so on, with corresponding numbers in order. Here, before adding remote origin, I have to initialize Git in this Docker examples folder and commit changes. Let me do that first. Git init. Now Git initialized in this folder. Now let me add all changes to staging area. Git add dot. Changes were added. So here I see all changes in all files. And here now let me commit changes. Git commit -m, commit message, Docker crash course, project files, like that. Let's commit. Changes were committed, and now I am able to add origin as specified here. Git remote add origin, added. Now let's rename branch to main, because now GitHub does not recommend to use master as a primary branch name, so let's rename it to main. And now let's push local main branch to remote, and this will actually create tracking branch, and local main branch will be connected to remote main branch. And here I see that a new branch main was created at the remote repository, Docker Crash Course. If I refresh page here, I should see all project files, NGINX, Python, Python custom, and so on. These are all files which you could reuse if you wanted to launch specific project yourself on your computers. Alright guys, that's it for this Docker crash course. I hope you enjoyed it, and see you next!